So welcome everyone to the next entry in MSI's summer tutorial series, Introduction to Linux and the Command Line. Uh, I am Nick Dunn. I'm one of the scientific computing consultants here at MSI. One of the folks, if you email the help desk and turns out you need specialized help getting your software or workflow up and running, I am one of the folks who can provide that help for you, just to give a sense of what I do here. A couple of logistical things. First, I will drop information about the help desk into chat here, link to a page containing location and contact information. If you are having trouble accessing or using MSI, that is your first point of contact. And you can visit physically in Walter Library, you can call in, or you can contact via email. There are also ways to set up appointments via an online office hours link. And you can see their active staffed hours there on that page as well. And then in terms of our schedule for today, we're going to be running from about now until noon for hitting the fundamentals of working with a command line interface. We might have a break in there for coffee and stretching our legs around 10:30. Then have a lunch break from noon to 1, and then we'll be going over using those fundamentals that we covered this morning to build more advanced workflows from around 1 to 3. Well, exactly 1 to around 3, depending on how things time out. Again, looking at likely break in there somewhere around 2. Then I want to also in chat post a link to the material that we are going to be going over today. This is adapted from a software carpentries course, Intro to Unix and the Command Line, or Intro to the Unix Shell, depending on when exactly you're engaging with the course. And we've added some MSI specific content in here to make some of the examples more relevant and to get to some more high performance computing relevant topics towards the end. The material there is structured with narrative content describing what's going on, punctuated with examples. And so it's a very good set of material to use for review. I will be walking through it today, sort of interactively working through these examples, and you are encouraged to follow along if you are able to do so, trying some of these commands yourself. Question in chat is login for that page. Do we need to set up an account? No, this will be your UMN login information. That is the UMN's on-premise GitHub. So you would sign in with the same UMN credentials that you use to access your email to get into that page. This might be the last time I deliver this material where it lives here. We are migrating to a different GitHub instance, but for now, it is behind that UMN login because that is a UMN specific GitHub. That question in chat reminds me that please ask questions in chat as we're going along. Hopefully, if you're able to run some of these examples, you'll run into some common errors while doing so. And it's a good thing to raise in the chat to get some clarity. Or if you have any questions about anything that I'm covering as we go, and I will keep an eye on that and try to address them as they come up. in terms of following along, I'm going to share a screen here. All right, so we'll share this browser tab. So if you do not have an easy way to access a terminal, or you don't have a preferred way set up yet, an easy way to follow along with our content today is to navigate to ondemand.msi.umn.edu. I posted that link in the chat as well. And that will bring you to, after you log in, to a page that looks like this. Then the fastest way to get a shell terminal from here, which is what we're going to be typing our commands in, would be to go to clusters and then agate shell access from this strip across the top. And that will drop us into a new tab that has this prompt that we can type things into, and the computer will respond. This is not how I'm going to be presenting the material today. There are some peculiarities for this terminal around presentation, difficulty with resizing and text resolution and what have you. It's a perfectly serviceable way to access the system. It's just not a great one to present from. So I'm going to go ahead and close that for me for now. And go ahead and stop sharing. Terminal I am going to share. That. And one additional logistical thing, since this is the terminal I'm presenting from, is the text displayed on screen here large enough to be legible for folks? Please indicate that in chat or a thumbs up, thumbs down reaction. One looks okay, a couple of thumbs ups. No one's saying that it's a problem. So we'll go ahead and proceed from here. Zoom, please stop taking over different chunks of my screen. Thank you. All right, so just the briefest bit of historical background before we jump into our practical examples. So the software that we're working with today is something that runs on top of Linux, which is in a family of software alongside Unix, which was invented in the 1970s at AT&T Bell Labs. Linux is, as I said, related to this and sort of branched away from this in the early 90s. And Linux is now developed by the open source community as a free operating system, free as in conceptually free, not necessarily free as in beer. Sometimes you do have to pay for it. And as an operating system, Linux has some big advantages depending on your domain. It is free, stable, extensible, and fast. And so software in these families, Unix and Linux, end up being the dominant operating systems for large-scale computing systems, like the high-performance computing cluster here at MSI. There are a lot of different flavors of Linux. Sometimes they're called flavors, sometimes they're called distributions, which are developed and maintained by different communities to fill different purposes. The one we use here at MSI is called Rocky Linux, which is a distribution that is designed to be fully compatible with Red Hat Linux. And Red Hat Linux is a distribution that is used heavily in enterprise platforms. And so by using Rocky Linux, we get some of the benefits in terms of applications supporting our platform without necessarily having to pay the same high support costs that would be available with Red Hat Linux. That's our brief historical and context blurb. Then in terms of getting into what we're actually interfacing with today, I've already run a command here. This is via a command line interface where I have some prompt. I type some text that the software running on the cluster interprets as a command, and then it does something based on that. Here I said echo hello, which means print the string hello to the terminal, and it did it when I ran it. This is the basic sort of interaction loop that you're going to be in with a command line interface. You enter some text that specifies what the computer should do. You run that, the computer does it, and then it waits for your next input. This is distinct from the graphical interface that folks are probably more familiar with, like a desktop that you interact with a mouse or a touchpad, or a touchscreen device like a tablet or a phone would also be graphical user interfaces. Those graphical interfaces, there's sort of a visible menu of options presented to you, either in terms of icons or literal menus, and you click or touch them in order to specify which of those options you want the computer to perform. This is fairly intuitive. You can see what is possible to do by looking at the screen, and then you select from those available options to perform a task. However, there are limitations to what you can easily represent visually, both in terms of the number of things that you can have on a screen at any given time, as well as the complexity of things that can be represented in an intuitive way. And we sort of sidestep some of those bottlenecks in the command line interface by mostly not attempting to present that information up front. There's a philosophy of expecting folks to read the manual, to attend workshops like this, to educate yourself on what is available to do. And then once you know those basics, you can very quickly start to compose advanced workflows that would be difficult or impossible to achieve using a graphical user interface by composing clever sets of commands in a command line interface like this. And in a research context, and research in high performance computing, we're going to want to exploit the benefits of this command line interface to let us perform repetitive tasks automatically and quickly, so that we don't have to manually intercede at every of a million iterations of some algorithm. Clicking a million times is just not something that we want to do in general. But if we can say, computer, do this thing a million times for me with a few lines of text, that is a much more approachable proposition. So the particular software that we're working with here today is a shell, as a category of software, and the particular shell we're working with is Bash, the Born Again shell. It's a pun on being derived from a shell written by Stephen Bourne, if you're interested in historical context there. And this is not only the one that we're using, it's also currently the most popular shell that you'll see in a lot of contexts. So what you're learning here should be transferable to other centers, other devices generally. So the anatomy of what we're looking at here, we first open the shell. I'll get rid of my previous command. We're going to be presented with something that looks like this. You might have a little bit more information on your screen depending on how your particular shell is customized, but you should at minimum have a prompt and a cursor. The prompt here, usually a $sign, but sometimes a percent symbol or something else, again depending on your customization, indicates that the shell is waiting for you to type some input. So it's just kind of idling there, waiting for your commands to be presented to it. And then the cursor here indicates where text will be entered. If you start to type something and need to sort of navigate back and forth through it, the cursor will tell you where additional text will appear, as cursors will behave in other word processing contexts as well. So then if our shell is waiting for a command, let's go ahead and provide it with one. Command ls that we're going to be using frequently today stands for list, which lists the contents of the current working directory that our shell is in. And if I run ls, I see that I get what I know to be a set of files and directories that are present in my home directory. You are likely going to see different output than this unless you are me and are running in my home directory. You'll see the contents of your own home directory wherever you happen to be running this. Now we'll intentionally elicit an error at this point as well, which we might run into if we mistype a command or enter a command that does not exist on our system. Let's say I was trying to type ls and I typed ks instead, just one key off on the keyboard. And because there is no command named ks, I get this indication from bash, an error, that ks is a command that is not found. Now, this can either happen again when you have a typo on an existing command, or if you try to run a piece of software that may be available somewhere on the system, but is not currently available in your session as it is configured. So we have MATLAB installed for use on the cluster, but I don't have it currently loaded into my session. So if I type MATLAB, I get that same command not found error. So if you see command not found, you've probably either done this typo, check the spelling of your command, or you need to modify your environment somehow in order to get the software that you want to use loaded into it. And for the second case, we're going to be looking at software modules and how to load and unload them as one of our later topics this afternoon. So put a mental pin in that, and we'll be coming back to it. All right. And today we're going to be working with some test data so that we have something to run our commands against. A lot of this stuff gets more interesting and informative when you have some real text, some real information to run your commands on, rather than just sort of imagining what it might be like if you were to do so. And so let's go ahead and download that data. So to do that, I'm going to paste the command that I'm going to run into chat here. I think. There we go. I make that a code block. That should prevent it from getting mangled in the formatting. Then we will run an additional command after that. And I'll run these on screen as well. I just want these available as a copy and paste resource for folks. Or in case something happens and the command is not visible on the screen. So these are a couple of slightly more specific commands than the ls that we were just using. And we're not going to be using either of these very much throughout the rest of our material today, but they are good for excuse me, grabbing the test data here. So we will type curl dash capital L, and then inside some double quotes, we'll type z.umn.edu/shell lesson data, separated with those dashes, then space, dash dash, output data dash shell dot zip. Taking a moment to make sure I type this correctly. And then I'll go ahead and run it. And what this is going to do is download from this URL the file that is stored there. And it's going to save it as a file named datashell.zip. And this doesn't take much time at all to run because this is not a particularly large file. Excuse me. Hopefully this frog in my throat clears before too long. And then if we run ls again, we'll see before running this, we did not have anything named data shell present with ls. If I ls again, I see now there is this datashell.zip file that has showed up. Then if I want to access this, I'm going to want to unzip this so it behaves as a directory with contents, and we'll get a little bit more into that in a bit as well. To run that second command, unzip datashell.zip. And this will give me an indication of the contents that are being inflated into this directory called datashell. By ls, I see not only do I have a datashell.zip, I have this other entity here, which I know to be a directory called datashell. And among other things, this contains a data set from a fictitious marine biologist, Nell Nemo, who we're saying has just returned from a 6-month survey of the North Pacific gyre, sampling gelatinous marine life in the Great Pacific Garbage Patch. Our fictitious data set here has almost 1,600 samples that Nell has run through an assay machine to measure the relative abundance of 300 proteins. And all of those almost 1,600 files need to be run through an imaginary program called GooStats that she inherited maybe from some postdoc who has since left the group. On top of doing that, she's got a paper submission deadline, so this has to happen relatively quickly. The problem is if we're using a graphical user interface, Nell would have to select and open a file with GooStats almost 1,600 times. If it takes 30 seconds to run each time, the whole process takes 12 hours of Nell's undivided attention. And people are bad at focusing intensely on things for 12 hours at a stretch, so mistakes are likely, which means that probably there'll be more than 12 hours, as either you're taking breaks to allow your attention to recover, or you are needing to go back and fix errors that were made during a too intense 12-hour session. And what we're going to build up over the course of our material today is how Nell could have her computer perform this task while she focuses her attention on actually writing the paper, which is sort of the ideal division of labor between a computer and a person. Computer does the automatable stuff, the person does the stuff that requires thinking. So with our data in hand and our toy problem set out, I'm going to go ahead and clear the screen, get rid of those visual distractions, and we will start looking at how we navigate files and directories. So I mentioned that we had downloaded that data and unzipped it to a directory. And there's some other directories present in my home directory. But depending on your experience using Linux or other operating systems at a particular level of sophistication, some of this terminology and some of these ideas might be novel. So we'll just make sure that we cover it here so everyone is on the same page. So we're going to introduce a new command here that we're going to use a few times throughout the rest of our workshop today, which is called pwd for print working directory. And what this does is it tells us the directory that our shell is currently looking into. So as we saw before with ls, this is the directory that is acted on by default by a lot of commands. That's sort of where our vision is sitting as we are navigating through this file system. If you are on MSI, and you haven't moved anywhere else, your response from pwd will look something like this, where you have /users, then /some number, /your username. This will look a little bit different if you are using your personal desktop for this. On Windows, you might have C: something, or on a Mac, it might be /capitalized users /your username. And if you're on a different Linux system, it depends highly on the configuration of that system for what this might look like. Another common one might be /home /username. But in all of these cases, the meaning of some of the components here are the same, where the slashes mean one of two things as they are proceeding, and then the text here are the names of directories. And the two things that these slashes can mean, the first slash always means the root directory. So this is the directory that contains all other directories on the file system. Then additional slashes beyond that are separators indicating distinctions between other subdirectories. So the meaning that we are seeing here is we have the root directory / contains a directory called users, which then contains a directory called 3, which then contains a directory called done0404, which is my home directory. This implies a sort of tree-like structure where we might have several subdirectories contained by the root directory here, which then may contain themselves several subdirectories, which then could contain several other subdirectories. And so everything sort of branches out and down from that root directory on the file system. And I have a couple of graphics here. I'll just use this one. Share my more different graphic here for a moment. So this graphic is related to the layout on a Mac system, but again, this is the meaning of our different components is the same. So we have a root directory / which contains a set of other directories. One of those directories is named users, which then contains a set of other directories. One of them is named Nell, after our fictitious marine biologist. And so if I wanted to specify the location of this directory in the same way that we just saw pwd specify my MSI home directory, it would be /users /Nell. And so we're implying a an analogous tree structure for the home directories at MSI, just with different names for our directories and an additional layer of numbers separating our users directory from the particular home directories. Just so we have a visual indicator of what is going on there. And then again, if we ls here, what we are listing is the contents of our home directory or the contents of the current working directory, as indicated by PWD. And some of these, as I noted, are additional directories. Some of them are files. Some of them might be links to something. Some of them might be executables. There are a number of types of thing that we could be looking at here. And it's difficult with the default amount of information presented to us by ls to figure out which is which unless you happen to have it memorized for the particular folder. To give ourselves a little more help with this, we can modify the behavior of ls. If we say ls space dash capital F, this indicates we want to classify the output into one of a couple of categories. And if I do this, the output changes a bit. We have trailing slashes after some of these entities. We have an asterisk after a couple of them, and then the rest of them have sort of no modification. And so what we're looking at here in terms of classification is additional directories that are in here are given this this slash. So Ansoff, calculations, code, desktop, et cetera, anything with this trailing slash, including our data shell, is a subdirectory inside of our home directory that contains other stuff that we can interact with. Things that do not have that trailing slash are some sort of file entity, like datashell.zip is a file that contains data, but that we cannot directly interact with a set of sort of directory navigation commands. And then these couple of things here that have asterisks after them are executable files. These are programs that can be run as commands on the command line here. These particular ones happen to be apptainer images. If you are interested in apptainer or containerization of software in general, or you become interested in it at some point in the future, I give a tutorial on that topic every semester. So keep an eye on the help desk tutorial schedule if you'd like to hear more about that. And then we can modify the behavior of ls further if we want to say, well, actually, I'm curious about the contents of the root directory right now because that's been mentioned. So I'd like to list and classify the contents of the root of the file system rather than my home directory, which we've seen a couple of times now. So to do that, we will say ls space dash capital F space, and then we will give a slash as our final component to this command. And when I run this, we see a number of additional directories. We see this new indicator at, which indicates a link on the file system to some other location. So for instance, bin is a shortcut to some other directory on the file system that contains some executables. And lib and lib64 are links to some other location that contains libraries that help applications run. Clear, and then we're going to think a little bit more about the anatomy of this command that we just ran, because this is a good representation of the type of command that we're going to be running today. It has all of the parts at least represented here. So after our prompt, the first thing that we type is the command itself. This is the name of the program that we are running. ls is the name of our program. Then we have an option, which is indicated by this dash, and then some letter. Sometimes this is dash dash and then a word, as we saw with curl, for instance. Dash dash output was also an option. And then the root directory here, indicated by a slash, is an argument. So options indicate modifications to how our command ls is running. And then arguments are either something that specifies how a particular option is going to behave, as in the case of output we saw before, output to a file named datashell.zip. In this case, our argument is indicating the target of the command. So in general, arguments are some sort of free-form input that we're going to type that sort of narrow down the scope of the behavior of the command, whereas options are these different things that we can sort of toggle on or off to change the behavior of our command. Now, there are a lot of ways to modify the behavior of ls via these options. And it's difficult to remember all of them off the top of your head. I only remember the small handful that I interact with on a regular basis. Sometimes, though, I need to do something a little bit different. Like, I think there's an option for that. Where can I look for it? So happily, most of our command line tools here provide a help output, which indicates all of the usage information that you could ever want about them. So for ls and for most of these other tools, we can get that to print if we say ls dash dash help, where dash dash help is an option that says ls, instead of doing anything else related to listing, just provide me with the usage information for the ls tool. If I go ahead and run that, it will print out a big chunk of text. So I'm just pausing and talking for a moment for folks who are typing to catch up. And then we'll get that text on our screen. And it's more than can be contained on a single screen. So I'm going to go ahead and scroll back here, where it starts off with this, this usage information, where it says you type your command, one or more options. This dot 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 here indicates you might have one or more, and then one or more files or directories here as arguments, and even specifies the default behavior, which is to list the contents of the current directory by default, which is what happened when we just ran ls without any modifications at the start of our workshop. And apparently it's sorting entries alphabetically for us, unless we specify some other sorting component. I see that question in chat, and we will address that in just a moment. And we can see then a list here of all of the different options that are available for ls. We can see classify. This is, whoop, skips me down if I double click. We have classify here, which we indicated with dash F. We can see if we want to, I often use H for human readable, and A to show everything, or L to show, lowercase l to use a long listing format, which provides additional information about the contents that are being listed. And there are different options available for sorting. If you want to recursively list subdirectories, there's a lot of ways that you can customize ls to your particular needs. And you'll notice for a lot of these, for classify that we've used as a particular example, there are two ways to invoke it that are specified. There is the single dash and then F that we utilized to run the command before. And then the longer form, dash dash, two dashes, classify, that is also available if we want to invoke it that way. These are equivalent in functionality, but the dash at the capital F here is faster to type. And you can see if you look at the one character versus many character for these, the most commonly used options, like all, directory, classify, human readable, those are provided this single dash, single character option to use in order to save you on typing. You can also combine these more easily if I wanted to say classify, show everything and make it human readable. I could do ls space dash capital F lowercase a lowercase h after a single dash, and that would be use all of those tags combined, versus having to say space dash dash all space dash dash classify space dash dash human readable. And so in general, when I'm aware of this shorter option, I will use it unless there is a specific reason not to, like making something clear to other users in a script that I'm passing on, or for other presentation reasons. Some of them that are used less frequently, like hide or hyperlink, do not have a shorter option available. And so you simply have to type these out fully when you utilize them. So in general, dash for this one character that you can sort of compose together, and I'll show an example of that in a bit. Dash dash when either that is not available or when you want to specifically type out the whole thing for usually a clarity related purpose. Does that make sense? Excellent. All right. And then we will intentionally elicit an error here as well, because there are a lot of these options available for LS. There's a lot of options available for most of these tools. And so it'll frequently happen that you might misremember the abbreviation for one, and you might say, all right, I want to do something that I think is indicated by dash J. So I'll say ls dash J, but that's not actually an option that was indicated there. And so I get an error printed to me. It says invalid option J, and then it points me directly to that help documentation so that I can figure out what it was that I intended to get out of the actual available behavior. Now, while the ls dash dash help command and dash dash help in general will work on MSI systems, they won't work everywhere, particularly on Macs, I believe, unless something has changed recently. It'll throw an error if you try to use dash dash help because of some slight implementation differences. On those systems where you get some error trying to run dash dash help, you can get access to the same information very frequently using the command man for manual, and then you give the name of the command that you want a manual for. If I run this, it's going to drop me into a little text pager application that's a little bit different than the shell, where I can scroll up and down with my arrow keys or page up and page down, and it's presenting me the same information but formatted slightly more nicely. So perhaps you might prefer to look at this anyway, because it's spaced out a little more reasonably for a human to go through and read it. And yeah, just page up and down through this. If you type a /, I can search through it. No, the pattern was not found there. Oh, because I was beyond it. It's a forward search, but it's highlighted human here. So if I were to go to the beginning and say human, it would pull me down to human there for the human readable component. And once you are done with this, you can exit by hitting Q to quit as indicated on bottom here. And it will drop you back into your shell prompt where you can type further commands. So I'll go ahead and hit Q here, get myself out of the man page information. Another way that is convenient to access this information is to pull it up in a web browser that maybe exists next to your terminal on your monitor. That's something that I frequently do. It's many times convenient to have a place to read the documentation, a place to run the documentation. And if you look up Unix man page name of command, so like Unix man page ls in your search browser or search engine of choice rather, that will get you relevant results that you can pull up as a reference to look at alongside. So there are a variety of ways to access this information, depending on what is convenient for you. So if we clear again, now we're going to start looking at and thinking about our data shell directory. So if we ls-f again, we remind ourselves that there is a directory here called data shell that we inflated from this datashell.zip that we downloaded. And we are probably curious by now what's actually in here. What sort of data are we going to be operating on today as our examples? It's not just that North Pacific Gyre stuff. We have a number of fun types of data. So if we want to ls the contents there, we can say ls space -f, and then we give data shell as an argument there. Say I want to list and classify the contents of data shell. And if I go ahead and run that, we see that we have a number of directories here: creatures, data, molecules, North Pacific Gyre, and writing. And then we have a couple of files in here, some notes, something to do with solar something in a PDF document, and something configuring pizza.cfg. And we could further say, ls-f data shell /data if we want to list and classify the contents of this additional subdirectory, which then contains some txt files and some additional directories, which we could, if we wanted to drill down, run additional ls-f commands saying /data /animal counts, for instance, if we were curious to do so. Now, we're going to be interacting a lot with the contents of our data shell directory and a lot with the contents of data. So we may want to actually change our working directory so that whenever we run a command, we don't have to type data shell /data /whatever thing we're interacting with. We can instead type something shorter that indicates the relative location from our working directory. So we can change our working directory to a different location by using a new command called cd, or change directory. Before we do that, I'm going to pwd to remind ourselves what our working directory is right now, our current home directory, and then I will say cd data shell, and I will go ahead and run that, and then I will say cd data. I want to change directories into data shell, and then I want to change directories into data. And now if I run pwd, I get that I am 2 layers deeper in my directory tree. I'm in my home directory /data shell /data. And if I run ls-f here, without having to specify additional paths, I can see the contents of this new working directory. And that will be convenient for me if I want to work with the contents of these txt files or with the contents of a couple of these directories at the same time, for instance. You can say, okay, but maybe I'm not actually ready to work with the contents of /data yet, so I want to cd back out into data shell. So a way that you might think to do this is say, okay, so we cd data shell and we cd data before. Let's cd to data shell again, because that's our parent directory. So let's say cd data shell, and that should bring me back to where I want to be, right? Unfortunately not. What cd is looking for here is it's looking for a directory in your current working directory by that name. And while when we run our home directory, we had a directory called data shell to cd into that was available in that working directory. In this working directory, there is no directory called data shell, and so cd doesn't know what we're trying to do there. Or rather, it knows what we're trying to do, cd into a data shell directory in this working directory, and it's like, that doesn't exist. I can't do that, so we're not going to do anything. So what we do instead is we're going to use a nice little shortcut here to cd into the directory containing the current directory. And we can use this regardless of what directory we're in, unless we're in the root directory, because then there's no directory containing it. But we'll say cd ... where ... is a shell shortcut, which means the directory containing this one. So here, the directory containing data, which is our working directory, is data shell. And if we run this, and then we run pwd, we see that we are, in fact, back in data shell, the directory containing data. And if we ls-f, we see the contents of data shell here. And if we wanted to, we could cd ... to make it back into our home directory as well. Now we can get a little bit more information about what's going on here, or at least how it's being implemented, if we modify our ls command slightly with an additional option. We can say ls space -f space -lowercase a. So we're classifying, and then we want to show everything here, which in this case, we want to show everything, including hidden files and directories, because there's a couple of hidden directories here that are of interest to us. So we see a little bit more content when we run with a -a to show all. We see this // and .. directories that are present. Also this .bash profile. This is a file containing some text that is analogous to one that exists in your home directory that configures some aspects of how your shell behaves. Configuring this goes a little bit beyond the scope of what we're doing today. But if you want to change the information that's available before your prompt or the default behavior of some of these commands, you can look up ways to customize your bash profile, and that will provide you with a variety of ways to sort of tailor your default experience as you interact with the system. But what's not beyond our scope today are these two directories here. // as I indicated, is a shortcut that indicates the directory containing this one. And on Unix file systems, this is actually a directory that lives in here that points one layer up in our directory tree. Then our / indicates this directory that we're currently in, which may not seem useful right now based on the commands that we've engaged with so far. But this can be useful and convenient in certain cases that we will look at later. And so that's why it's provided for us as a shortcut. Now, specifically, what -a is revealing here for us are all of the files and directories that are prefixed with a dot. So if you have files or directories that are named, their first character is a dot or a period, then they are not going to be visible by default when you run ls. And that is because there are a lot of configuration files and directories that may need to exist on a Linux system, probably a lot more than you are likely going to want to engage with. For instance, if I cd to my home directory and I ls -f-a, you can see that I've got dozens and dozens of these directories, and some additional files that are related to specific properties of a bunch of specific software, and different functions of the operating system as well. And most of the time, I don't want to look at this stuff. It's just saving configuration information from when I last ran something. And so the default behavior of ls-f showing me only the stuff that I intend to interact with is preferable in most of those cases. Now, I will also demonstrate here the combination of those options. So we have been typing ls-f-a in order to elicit this behavior. Because these are the single character options, I could also say ls space -fa, and this is equivalent to saying ls space -f space -a. And so you can remember maybe some small number of characters that follow the dash for a way that you frequently run ls. So just to prove this works the same, I'll run it again, and we do indeed classify all of my hidden stuff. A common way that I will run ls is I want to do ls-l for long output, h for human readable, and a for show everything. And so what this does is it shows a slightly different formatting of all of this stuff, with some ownership and size information presented as well. A little bit overwhelming in the home directory here with all of these bits of configuration. And we'll look at how to interpret some more of this information that's being presented here later. But just to demonstrate another common combination of those single character options. All right. We'll go ahead and clear that, and we'll cd back into data shell. And we'll pwd, and we'll ls-f to remind ourselves where we are. All right. Now, so far we've used cd with a particular directory as the target. But like ls, we don't necessarily have to. It does have a default behavior that we can use that is sometimes convenient. So I'm currently in data shell here, as we're seeing from a working directory. And if I run cd without providing any additional arguments, then it runs. It's perfectly happy to run, doesn't throw me an error. So it's changed my directory to somewhere, and we can check where that is by running pwd. And what it's done is it's gone back to my home directory. And that is the default behavior of cd without any additional specifiers, is you'll cd from wherever you are back to your home directory, which can be convenient if you are exploring a deep file tree, or you're just somewhere very distant from your home directory and you want to reset back to the location that you were when you logged in. Is a very common thing, and that's why the default behavior is as such for cd. And then if we want to cd a couple of layers deep at once, so we had done this in a couple of steps before. We'd done cd data shell, cd data. We can specify, as we were able to do with ls, as many subdirectories as we want, continuing to chain. So data shell /data is sufficient for our purposes here. If we run this, we are directly going from home directory to a subdirectory of data shell because we specified it precisely. If we ls-f just to convince ourselves, yep, there's the contents we expect to see there. Now, sometimes we are in file or rather directory trees that are not closely related to each other. So it's not easy to say like, oh, I want to cd, dot dot slash to get near there, or I want to back up a couple steps and then drill back down. I'd rather type the exact location that I want to go to rather than have to figure out relatively where I am compared to it. And CD also allows us to do that. So let's say instead of doing CD dot dot to get into data shell, we could type the absolute path to it starting from the root directory, cd slash users slash 3 slash done 0404 slash data shell. And because we're starting from the root of the file system, we can fully specify the location. And that drops us in exactly that spot. So these absolute paths are also available to us if these relative ones are not convenient with the dot dot slash and then choosing a name of something that is present in whatever working directory context we are in. Sometimes the relative ones are easier, sometimes the absolute ones are easier. Both tools are available to us. Got two other shortcuts for file navigation to mention here. The first is often we want to indicate things that are relative to our home directory. Like there's a desktop and a downloads directory in there that people will frequently use. And you might want to use them from some other directory that's not closely related. So in order to help facilitate that, there is a special character tilde. So we'll say ls tilde right here. And what we see is this is printing the contents of my home directory again. And that's because tilde is expanded by the shell to mean my home directory. So it expands to user slash 3 slash done 0404 as is configured on our system here. And if I want to, I could say ls tilde slash, let's see. I think there's nothing in desktop, but we will. Yeah, nothing in desktop, but it doesn't throw me an error. Do I have something in calculations? I should have something in calculations. So if I ls tilde slash calculations, we can see the contents of that calculations directory. And I could do additional drilling down if I wanted to as well. Then another character that is useful for shortcuts is the dash character or the minus sign. So I'm going to clear pwd. I'm here in data shell. And let's cd into calculations, and then we'll go into CUDA check. And I pwd and I say, okay, I'm in calculations, CUDA check, but I actually don't want to be here because this is not related to our current tutorial material. I'll be back in data shell. So if I say cd dash, what this will do is it will move me back to the last directory that I was in, sort of regardless of where it is relative to my current directory. So it tells me here that it's gone back to data shell. And if I pwd and ls-f, I see that is in fact correct. And if I then change my mind and say, oh, actually, I want to be back in CUDA check and do something, I can say cd dash, and it'll take me back to CUDA check, which was the last directory that I was in. So you sort of flip back and forth between two locations, which is sometimes convenient to do. But I want to probably be in my home directory slash data shell right now. So I'll head back there for the moment. And then one last little bit here before we take a quick break. here this, pwd, ls-f to orient ourselves. Let us introduce a handy little feature that I have been using sort of reflexively through this, where you've seen like maybe more text than you would expect appear more quickly than you would appear based on my otherwise visible typing speed. And that is tab completion. So let's say I want to look at the contents of our North Pacific Gyre data. I could type out ls-north Pacific Gyre, and then I could say ls North Pacific Gyre slash 2012-07-03. And then if I wanted to interact with a particular element here, I could type a different command, North Pacific Gyre slash the date slash the name of the file. That gets tedious to type, and it's easy to make a typo when you're doing that. So we could CD into this, but that's not always the option that we want. And even if we are CDing into it, we don't always want to type the whole thing. So a handy little shortcut is if we say ls space, and then we type the first character of what we want to interact with, and we hit tab, it starts to fill in the rest of it to give me an NO here. And if I hit tab a couple more times, it gives me a couple of additional options that match that NO pattern here. And so what tab is trying to do for me here is autocomplete what I am typing. So if I type N and hit tab, it says, oh, there's two options with NO. So we'll go ahead and give you that O. And then if I continue hitting tab, it shows me those two options. And if I want to type in R at this point, and then hit tab, it fills in the rest of it for me. And then if I hit tab again, there's only one directory in North Pacific Gyre, and so it simply auto-completes to that. So that can save a lot of time. If I wanted to directly get a tab completion here without having to sort of explore, because I know it's present, I could say ls nor, because that's the first point of difference, hit tab, and then run the command. The tab completion is a good way to avoid typos because it won't tab complete to something that doesn't exist. Whereas I might make a mistake typing North Pacific Gyre a dozen times, the autocomplete will not make mistakes in filling that in. Another little shortcut here that I will debut as well is if we want to recall a previous command, we do not have to type it again, no matter how convenient tab completion makes for us. We can simply hit up on our keyboard to recall the last command. If we wanted to run it again, we could hit enter or return to do so. And if we want to continue scrolling back through our previous commands, we keep hitting up and we go through which commands we like and we run the one that we want. And then we can hit down to go to more recent commands to sort of toggle through our history. And so something we'll see a little bit as we proceed here is I'll type a command, say, okay, I want to modify that a little bit. I'll hit up to recall it, I will modify it, and then we'll run it again. So tab completion and recalling last command are a couple of things that we'll want for convenience as we proceed. What questions do folks have about navigating our file system here? A question in chat here. If you have a file name with 2 words, do you have to use quotes? Are you asking about if you have a file name that includes a space, like ls my space data? Yes. And you can see that I have reflexively used quotes to do that. Yes, you need to either use quotes or use an escape character to indicate that that space is part of the file name rather than part of the command. And we'll look a little bit later at how this is parsed in a couple of contexts, but you do need to do something when you have a space in your file or directory name to tell Bash that this is not a meaningful syntactical space between parts of your command. Because if you do not include that, based on what we've seen so far, if I say ls my space data, these are two different parts of a command for ls that wants to list the contents of my and the contents of data. And there's no such thing named my, and that we do have data here, so it can't list my and it does list data. And if there's something called my space data, it's ignored entirely. But if we enclose this in quotes, we'll see, okay, now it's trying to interact with something named my data. We could also use a backslash to indicate the space is a part of the file name, interact with it in that way. I will advise in general, when you have control over the file names, don't use spaces. It gets a little annoying. But if you have to, these are the two ways to do so. Great. I would like to, at this point then, do a quick 5-minute break. We will be back at 20. So we can all hydrate, caffeinate, etc., and come back to look at working with files and directories. I'll see you folks in about 5 minutes for that. Alrighty, folks, welcome back from our short break. Let's go ahead and charge ahead with our material. So we've just looked at navigating the file system. Now we're moving on to the next section, which is which is rather working with files and directories. So we'll go ahead and clear. We'll remind ourselves where we are with PWD. Working directory is currently in data shell, and ls-f will remind us the contents therein. Now, we might want to, make new directories, make new files, move stuff around between different directories, rename files. And so that's the content that we're going to be looking at here. How do we do these tasks via the command line? The first one we'll look at is how do we create a new directory? The command for that is mkdir, stands for make directory. And it takes as an argument the name of the directory that you would like to make. In this case, let's make ourselves a directory called thesis, which will hold our fictitious, for the purposes of this workshop, thesis related documents. And then if we ls-f, we see that a directory called thesis has newly been created, even though there was no output after we ran makedir thesis. And makedir is another one of these commands that unless there is an error, it will not print any output for you. So if it runs successfully, it has made the directory as requested. And so we see, in fact, it has done so here. Now I'll reinforce here the naming convention spiel that I started, where we want to avoid spaces where we can. Where possible, substitute them with dashes or underscores or dots. Underscores and dashes are slightly more standard. I prefer underscores just because of my historical context. But anything that's not a space or a special character is likely to do you better than trying to deal with how spaces and special characters are interpreted by a bunch of different tools in the command line context. Do avoid starting your file names or directory names with a dash because that'll be treated as an option by your different commands unless you use those quotes, which again becomes a little bit annoying. So ideally, we're sticking with letters, numbers, the period, character, dash, and underscore, sort of as our palette for naming things. Sometimes we get data that has different naming conventions, and we can work around that with those quotes, but it's kind of a hassle. So when we can choose to do so, letters, numbers, and those three separator characters. Then if we ls-f on thesis, there's nothing in there, unless we say ls-f, and we'll bring our cursor back with the arrow keys to make this ls-fa thesis, and we see, aha, automatically created are the // and // components that we use as shortcuts to navigate in and out of these Unix directories. But aside from that, thesis is fully empty. There's no novel content in there that we've placed yet. So let's place some content. So we'll cd into thesis. And then we're going to open up a text document in a text editor. Here we're going to be using Nano because it is easy to work with for a workshop. More commonly on our system, folks might be working with either Vim or Emacs, both of which are highly extensible to your different text editing or programming or personal organization needs. Highly tunable, the both of them. And going into the differences, philosophical and practical between them is beyond the scope here, but know that it's a fairly heavy debate about what is the best text editor and why. And Vim and Emacs are usually at the head of the pack there. We're going to circumvent that whole debate today by using Nano. And we're going to say space, draft, draft.txt as the name of the file that we'd like to open. File doesn't exist yet, so Nano is going to create an empty file by that name, and then we're going to start typing in it. So when I run this command, it's going to drop me into a new interface, which is that Nano text editor, which looks a little bit different. We don't have a prompt anymore. We do still have that cursor. And this is just a little text editing thing where I can type stuff. So for my thesis, I might type, it's not publish anymore. It's share and thrive. Just as some sample text to include in my thesis draft. Now, let's say that this is all I want to write for my draft right now. I'm not feeling especially inspired. And I want to exit and have this saved to draft.txt. The way to do this, as is indicated in sort of an arcane way down here at the bottom, is if we hit Control X, that will start us the process of saving and exiting. This symbol here, the caret, indicates the control button in our syntax within Nano. And then they've capitalized it for clarity, but we do not have to hit Shift or have caps lock on or anything. Just Control X is sufficient to get the exit behavior. It's going to prompt us if we want to save the modified buffer, because we did write some text in here and wants to know if we would like to actually save it or not. Going to hit Y for yes, as indicated by these options here. And then it's going to prompt me for a file name to write. It auto-fills in what I included on the command line. And I would, in fact, like to save it to that. So I'm going to hit Enter to confirm writing to draft.txt. And then if we ls-f now, we have this new file in here called draft.txt that contains that text. If we, for some reason, need to create an empty file instead of a file containing text, then a text editor is probably overkill for our purposes. There's a different command that we can use called touch, which will create an empty file of a name at a location. So for instance, if I wanted to create a file called my_file.txt inside thesis, I could run touch my_file.txt. And then if I ls-f, we have draft.txt as before. Then we have this empty file, myfile.txt. As to why you might want to create an empty file, sometimes it's a convenient placeholder, like you're going to come and write some text in here later. Or maybe the presence or absence of this file is something that modifies the behavior of a program that is running in this directory, or will be a place that a program will write some output in this directory, but only if the file already exists. So there's a number of possible reasons in these various command line workflows why you might want an empty file. And touch is one way to do that. All right, so we've made ourselves a new directory and a couple of files. Now let's look at moving those around. So we'll first cd to ~data shell, which is one way to cd to the data shell directory here. And if we --f, we see thesis is there. I can say, all right, so maybe that the contents that I had in draft right there, that's not actually a draft of my thesis. That is maybe some contents that are quotations for my thesis. Still related, but I want to change the name of that document. The way that we change the name of the document on the command line is we move that contents from its current file name to a new file name. And we do that movement with the command mv, which stands for move. So we'll move from thesis/draft.txt, and again, I'm using tab completion here, to thesis/quotes.txt. And mv is another of these commands that does not produce any output when it runs successfully, similar to mkdir. And if we ls-f thesis, we see thesis is no longer there, but quotes.txt is there. So we didn't create a copy of it at quotes.txt, we actually moved it, and the original is no longer present by that name. Now, we can also change the location with respect to the directory tree using the same mv command. So it can either do renaming or this sort of logical movement. And so maybe we say, all right, those quotes are not actually related to my thesis. So what I want to do is mv thesis quotes.txt, and I want to move them into data shell, this current directory that I'm in. And so here's the first place where we're going to use this one dot shortcut to indicate move this file here, rather than having to type it out explicitly. And if we ls-f, we see there is now a quotes.txt that is present here that was not before. And if we ls-f thesis, quotes.txt is no longer present in that directory. Then sometimes we'd rather copy than move a file. And there's a different command for that, cp for copy, where we might say, okay, quotes.txt, like actually, I want to keep a copy of it out here because I need it for something else, but I should have a copy of it in my thesis after all. I just want it to be more official sounding when it's in there. So we'll copy quotes.txt to thesis, and then we will say that I want the new file name to be quotations.txt. So I'm copying it from its current location to a new file in a new location. And I ls-f here, quotes.txt still exists. And I ls-f thesis, we have now this quotations.txt that has shown up. I can say, okay, so if I can copy files, maybe I want to copy my entire thesis directory to make a backup of it. It's a reasonable thing to think to do. To do this, I cannot simply say cp thesis backup. This because cp does not work without slight modification on directories. We can directly type the file and the destination for files, but for directories, doing that requires a slight modification. And it tells us what that modification is here. -r was not specified, which is a recursive flag that we'll need if we want to copy a directory. So if I ls-f, we see there is no thesis backup yet. But if I hit up a couple of times to recall that cp command, and I go back and I say, okay, cp space -r space thesis. So I'm adding in this recursive flag that it mentioned here. Now I don't get any kind of error or warning. And if I ls-f, I see that I've got thesis backup. If I ls thesis and thesis backup, and I see both of these exist, and they both contain my file and quotations.txt. The requirement of this -r thing is convenient here to avoid accidentally creating copies of many, many files or very large files that might be contained in a directory. It introduces some intentionality. You say, I want to copy this directory and everything in it, and I definitely want to do that recursively. So this -r is sort of a stop and think feature, is one way to conceptualize it before fully copying over a directory. Now we've created, we've moved, we've renamed, we've copied. A missing operation is removing files and directories. What happens if we want to delete something? So let's say, actually, I do not need quotes.txt outside of thesis because I have thesis backup, which has quotations.txt, so I don't need the separate backup of quotes. So I would like to get rid of that file. So I will say rm, which stands for remove, quotes.txt. If I do that, nothing is printed. If I ls-f, quotes.txt is no more. Now, I will say at this very early stage of introducing you to RM, when we delete things using RM, it does not put it into a trash can. It does not put it into a recycle bin. It simply deletes it. It is gone. Um, so we want to be exceptionally careful when we use the RM command that we are not using it on irreplaceable data or code or something that we actually don't want to delete because recovery options are very limited after that point. Depending on where the file is, if it's in your home directory, we do offer snapshots that provide, periodic backups of some things, but it's not something that you should rely on. You should instead be safely using the RM command to avoid deleting things that you don't want deleted. So extreme caution when using this. One way to do that would be to use it with the -i flag for interactive. So let's say I want to, as an example, rm-i thesis, scroll back up, quotations.txt to potentially remove the quotations.txt. It will prompt me for this, do I want to remove the regular file quotations.txt, yes or no, which gives me the opportunity to think like, do I actually want this one deleted? And in this case, I can say, no, I don't actually want this deleted, and we're done from that point. And that's, maybe less useful when we are working with a single directory, but it becomes more useful for sort of reviewing everything that is happening when we delete an entire directory. So for instance, if we wanted to remove thesis, having made a backup, typing rm thesis makes my skin crawl, but we'll do it for the sake of example here. Say, okay, I want to get rid of thesis knowing I have a backup, and we'll just restore from the backup later. This also doesn't work as is. Because like with CP, RM has this feature we can think of as sort of a convenient safety feature that we need to specify, I want to recursively remove this directory and all of its contents, and I have to make an affirmative decision to do so when I compose the command. So if I recall this command, I say rm-r thesis, this would recursively remove thesis and all of its contents. Let's make this a little safer by having it be rm-ri thesis to interactively remove all of those things. And then we'll step through what is actually being removed, and we can confirm or deconfirm each of those different components. So it's asking me, do I want to go inside directory thesis in order to delete its contents? We'll say yes. Do I want to delete regular empty file, myfile.txt? Sure. So Y for yes. Do I want to remove regular file quotations.txt? Yep. And then do I actually want to remove the directory itself? Also yes. And so it steps through in this way, and I have a chance to think like, what is actually in here? Can I safely delete that? And if I say no, then it doesn't, and that it remains after the command is run. In this case, I did want to remove everything. And so if we ls-f, we see thesis is no more, its contents are gone, forever lost to the wind, and then thesis backup is the only sign that we had done any work on our thesis today at all. Which again, a bad situation to be in, but sometimes that's what we need to do. Let's see. All right, so let's demonstrate another situation where being very careful about RM might be useful. We cd into molecules, we ls-f, we have a number of these .pdb files which contain structural information about a handful of different alkanes here, like the identity and position of atoms within them. And let's say that we want to perform operations with some subset of these files. Like we'll use ls as our example, and we'll say ls, I want to list all of the files in this directory that end with .pdb. Let's say there are like hundreds of files in the directory. Some of them are .pdb and some of them aren't. I only want to see the .pdb files. I can type ls space *.pdb, where this asterisk character is a wildcard that matches 0 or more characters at the position it's put. So this matches any file that is either named .pdb or has any characters preceding .pdb. And in this case, that matches all of our characters because all of them start with something and end with .pdb. So that's maybe not an interesting use of the wildcard. But if I recall this and I edit it, and I put a P before that asterisk, this will match only those files that start with a P, then have 0 or more characters and end with .pdb. So this would match p.pdb, and it will also match, as we have here, pentane and propane.pdb. And you could put this in different positions to sort of compose a different thing. We could say this should, anything that contains at.pdb, 0 more characters than a t, then 0 more characters.pdb. And we get ethane, methane, octane, pentane, omitting cubane and propane, which do not contain a p inside. We can get a little clever with these asterisks to interact with subsets of files. We have a second wildcard character, which also lets us get clever in similar ways. The question mark, which matches exactly one character at that position. So if I say ls question mark ethane .pdb, this is only going to match methane.pdb because it's one or more characters. We need to have some character in place of the question mark. And because methane has an M there, it matches. And we can combine question marks. So we can say ls 3 question marks ane .pdb, and then we get all of them that have 3 letters, and then ane.pdb, cubane, ethane, and octane.pdb are all represented here. And we can mix and match question marks and asterisks together to compose arbitrarily complex wildcards to match whatever subset of things we want. And you can imagine that if the thing we were doing with our wildcards was figuring out like a subset of files to delete, that we might want to be exceptionally careful that we had composed that wildcard expression correctly. And so we could use rm-i on the wildcard expression that we have in order to interactively say, do I want to delete this one, yes or no, and sort of check our work as we go. But I also like to compose my rm commands starting with an ls. So, and we're not going to remove any of these files today, but for the sake of theory, let's say that we wanted to delete all of the files that match this particular wildcard sequence. I would at first compose it as I have done here as an ls, and then I would review the things that matched it with ls after running it as an ls. So I'd say, okay, I think I want to delete everything that's question mark, question mark, question mark, ane.pdb. Let's ls those, and I will double check that those are what I want. If that's the case, I would hit up to recall that command, replace ls with rm, and then rerun the command to remove those things that I had verified. Just another way to have sort of a careful workflow as we're working with rm. But again, we need these for later, so we're not going to delete anything now. Let's see. Then let's cd dot back into our data shell. And we'll take a look at file permissions. So ls-f, we have, we'll just start thesis backup. Let's create ourselves an empty file that we can look at the access permissions on and then modify them. We'll touch my data.txt. And then we're going to use ls-l to get that long output that we had seen before. And I only want to look at it for my private data.txt because I'm not interested in ownership of the rest of these right now. It takes up a bunch of screen space. So we'll say ls-l my private data.txt. And then we get this more detailed output where we have the file name, the date when it was last modified, the information about the size of it. And then we have this information that's out front here that gives us a little bit of information about who owns the file and who is able to change it and access it in what ways. So the specific permissions flags are these characters here. And we'll look at interpreting those in just a moment. But those are relative to these strings here, which are the username of the owner of the file, in this case, done0404, that's me, and then the group that owns the file, in this case, MSI staff, which is a group that contains support staff at MSI. And so I am the owner of this file, and the MSI staff group is the group that owns this file. And then, so we can think of three separate groups of users of a computer system with respect to this file. There's me, the owner of the file. There's the group that owns the file. And then there's everyone else. And those are the three groups, the user, or the owner rather, the group, and then everyone else besides those. And these permissions are arranged in such a way that they indicate permissions for the owner, the group, and everyone else. The very first character in this is a bit of an exception. So that leading dash there, this would be a D if it's a directory, a dash if it's an object file, an L for a symlink, in some cases, but mostly we're going to just be seeing dashes for files and D for directory in what we're looking at today. So this is the type of thing that we're looking at in some sense. Then following that, we have three sets of three characters. We have right now RW dash, then we have dash dash dash, and then we have dash dash dash. And each of those three sets of characters corresponds to one of those groups of users. This first three corresponds to the permissions that I, the owner of the file, have. That second cluster of three corresponds to the group who owns the file. What permissions do they have? That final group of three corresponds to everyone else. And then positionally within those three dashes, it can either be an R or a dash, a W or a dash, an X or a dash. And right now we have RW dash. So I have RW permissions as the owner of this file, don't have X permissions, and no one else, either in my group or any other user on the system, has any permissions with my private data file. So it is somewhat private in that context. The R, W, and X permissions correspond to read permissions. Can I view the contents of this file? Write permissions for W. Can I modify the contents of this file or delete the file? And then X permissions, which are execute permissions. Am I allowed to run this file as a program? For a .txt file, that's maybe not so meaningful. And by default, we don't have that. All we can do is look at the contents and modify the contents of the file, which is what we've been doing by default. Now, sometimes we might want to say, okay, I actually want other people to access this data in some way, because maybe it's useful to other members of my group, or maybe it needs to be available to some collaborator who's also on the system. And the first thing you need to do when you are considering that sharing is make sure that the file is stored in some location that everyone has access to. Most commonly, this would be somewhere in your projects directory. So like a project standard MSI staff is a location where you can put MSI staff projects and associated data. I have a user directory in here that's hidden, so do the rest of the MSI staff. And then I can put contents in there that other people can access because right now we are in a subdirectory of my home directory. No one else has access to this by default, and I can't make them have access to it on MSI systems. So I have to put the file I want to share somewhere else. That's, again, either projects for the specific group that you want to share with, or maybe in a Scratch directory if you want to share it more broadly temporarily. It really depends on your workflow. But for now, we're not going to worry about the location. We're just going to worry about these permissions. So we'll ls-l my private data.txt, and we'll say, okay, maybe I'm the only one who should be able to both read the contents of it and modify it, but maybe my group should actually also be able to look at the contents. Maybe it's relevant to the project that they're in. So I have a command available to me called chmod. Don't know what exactly it stands for. This means, to me, modify permissions. And we say G plus R stands for I want my group to add the read permission on my private data.txt. Now if I ls-l my private data.txt, we see that we've skipped one. This is my user execute permissions. That stays blank. But the next one, in our next triplet of characters here, has gone from a dash to an R. So that means everyone in MSI staff is able to read this file if they have access to where it's stored. And I say, okay, maybe actually everyone in my group should be able to write the file as well. So I can run a further chmod G plus W on my private data.txt. Now if I ls-l my private data, now everyone in my group has the same permissions that I do on the file. They can look at the contents, they can modify or delete it. And maybe that's exactly what I want here. Or maybe I actually want this to be more open. For some reason, maybe I want everyone on the system to be able to access my private data. Doesn't feel very private anymore. Perhaps a file name change is warranted. But we can change the permissions to that regardless. So we can say chmod O, which stands for other, plus RW. So we can add two permissions at once. We can say for everyone else, for others, add the read-write permission to my private data.txt. And if I ls-l my private data.txt, we can see everyone's got read-write permissions. And say, okay, well, that's actually maybe not a great way for a file to be. If anyone can modify it, certainly not private, and maybe I can't trust the file for very long, depending on where it's stored, and who might accidentally modify it. I say, okay, so everyone can read it because I'm ready to publish this, but no one should be able to modify it, including me. I don't want to accidentally modify it in the future because it's reached some final state. And I can say, all right, I want to get rid of write permissions for everyone. Say chmod A minus W. A stands for all, so all three of our roles here. We're going to subtract the write permission for my private data.txt. And then if we do ls-l my private data.txt, we see that everyone has a read permission, but no write or execute. So just a couple of modifications to permissions that you might do there. I will also ls-l just on this directory in general, data shell to show us some of the other permissions setups that you might have. We see for our directories here, they do start with this D to indicate that they are a directory. And these all have the X flag, the X permission set for all user roles who are supposed to access them. And while for files, the X flag indicates that this is a program that you can run. For directories, this means this is a directory that you can navigate into. You can look at the contents, you can list, you can cd into it, you can interact with it as a directory. So if you have a directory that you can read, you almost certainly want to also have it be a directory that you can execute. And so you'll frequently set directories to r-x for a role that you want to be able to view the contents. Whereas you probably for data files might only set it to R for the role, so you want to view it. And then very frequently, you have the right ownership is only, or the right permission rather, is only available to the owner of the file. Again, the username listed here. So that's a quick overview of file permissions and how we would change them. Again, the file location matters a lot for this. But the chmod command can be used to sort of granularly change who is able to access a particular file and how. What questions do folks have about working with files and directories or file permissions in particular? Seeing and hearing none so far, we'll go ahead and, well, 4 minutes till break. Let's go ahead and break the 4 minutes early for lunch. I'm not going to be able to get a significant chunk of our next topic, pipes and filters, before then. We're going to look at how we can combine the output of different commands to compose little one-line workflows and start really increasing our capability to do things that are useful with the shell. So preview for the fun stuff after lunch. But let's go ahead and stop here for now. We'll come back in an hour. We'll say back at 12:57. And if you think of any questions in the meantime, feel free to drop them in the chat and we'll discuss them when we get back. Otherwise, hydrated, caffeinated, got some calories so our brains can function for the afternoon material. Which is right, pipes and filters. We're going to start building some workflows by composing together commands to do some more powerful things than a single command alone can do. Before we proceed, what questions do folks have from the material we covered this morning? All right. Oh, yes. Sometimes there's a trailing slash at the end of a path. Does it matter if that's included? Is a question from chat. So I'll be talking if we WD ls-f to orient ourselves here. If I were to start typing molecules and hit tab to tab complete, it gives me this trailing slash. Or similarly with thesis backup. And in the context we have been seeing it, that trailing slash for our ls, for our cd, for what have you, does not matter whether or not it's included in these commands. I can ls data or I can ls data, and it's the same for me in either context. The reason that it's showing up sometimes in tab completion is so that there's an easy visual indicator for us to know if there are additional things that we might want to type and complete. So it's showing up here. I say, oh, what else might I complete? Because this is a directory, I can say, all right, I might want animal, and then that matches two things, animal counts, animals.txt. So it's a visual indicator here. Um, so it does not matter for directories right now if we are having a trailing slash or not. There are certain tools and I guess often scripts that you might see associated with research code that will be sensitive to the presence or absence of a trailing slash. You'd have to refer to their particular documentation because that's not well standardized. So it does sometimes matter, but generally it should not, is the answer that I will provide. Great. I didn't see other questions show up during that discussion. So let's go ahead and proceed with the material. If other questions do occur to folks, please feel free to drop them in the chat. And again, I'm keeping an eye, so I will try to address them as they come up. We'll go ahead and clear. ls-f. We're in our data shell directory. And we're going to cd back into molecules and ls-f to look at these PDB files. Now, something that we might want to do if we have a directory full of molecules, which are represented by these PDB files, which lists the number of, or not the number, it lists the atoms in their positions, the types of them in their positions. So, for instance, let's introduce a new command cat for concatenate, and this is used for, you might provide a list of files afterwards, and it would print their contents one after the other, so you could save them as a combined document. But it's also a convenient way to print out the contents of a single file if you only provide one file. So we'll say cat methane.pdb to look at its contents. And what we have here are a couple of lines that have some header information, the name of the molecule, some author information. And then we have these atom lines, which are the identity of several atoms and their relative positions. And then we have a suffix that says the file is over. And this is a standard way of representing the sort of atomic position information for a molecule. And all of these PDB files have similar contents, except they're going to vary in the number and type of atoms, as well as their relative positions. So let's imagine that we had a directory that was full of dozens, hundreds, thousands maybe of PDB files. And we want to know what is the smallest molecule that is present in this directory of PDB files. And we'll say smallest by number of atoms. That's something that's immediately approachable for us right now. Well, the number of atoms in one of these molecules is going to be related to the number of lines in the file, minus the header and footer component. And the header and footer are going to be the same for every file. So if we look at trying to sort by how many lines we have in these files, we'd be able to pick out the shortest file by line count and say, ah, yes, that's our smallest molecule. So how can we use the command line to do such a thing? Well, first, we need to introduce a tool that allows us to get the number of lines in a file. So we'll bring in a command called wc for word count, which takes as an argument the name of a file, or one or more files. We'll give it one file to start. And the default behavior is it gives us three numbers and then reported next to the file name, where this is the number of lines in the file, the number of words in the file, so space-separated entities in the file, and then the number of characters in the file is our largest number here. And it can operate on one or more files, like I said. So let's utilize that wildcard character, the asterisk, to have it word count all of our PDB files here. And say WC asterisk, not ampersand, dot PDB. And that will match all of our PDB files because this is 0 more characters. And we get this length information for all of our PDB files. And then there's also a total that is provided by WC that sums up everything that has been queried here. Now, if we're interested only in the number of lines as an analog for the number of atoms here, as our most direct measurement of sort of the size of our molecule, we can say WC dash lowercase l as an option to say only give me the line count information. Say asterisk dot PDB. So modifying this previous command to give only line count information, and now we've sort of filtered it down to give us this list of PDB files and then the number of lines in them. And by inspection right now, because the number of lines, or the number of files is small, we can sort of at a glance tell which is the smallest, which is the largest. But again, let's pretend we're working with a larger data set here because that's where things are computationally interesting. Probably not frequently working with batch operations on just like six files. Be dozens at least. So the next thing we might want to do is say, okay, if we have an arbitrarily long list of lengths like this, we might want to sort it so that we can see what is the smallest up at the top. One way to do this would be to save the results here to a file rather than putting them in the terminal output. And then we can use a different command to sort the contents of that file. So to do that, let's hit up to recall that previous command, and we're going to add the redirection operator with a greater than symbol. And then we're going to give it the name lengths.txt as the new file that we want to create that will contain this information. With this redirection operator, it's going to create a new empty file of this name, regardless of whether or not a file of that name exists currently. So this will overwrite an existing file named lengths.txt. So just take care when using this particular redirection operator that you intend to overwrite an existing file if indeed one does exist. There's a different operator for appending, and we'll view that in a little bit. But right now, let's run this. And we rerun the same command and we redirected the output to lengths.txt. Nothing was printed to the screen because we redirected the output. So we captured it before it came to the screen and said, go in this file instead. So if we say cat lengths.txt, we see that file contains the contents that we would have otherwise seen printed to the screen. And we have this lengths.txt file present via ls. Now, to sort lengths.txt, we can use a command which is helpfully named sort. And we're going to use an option on this, -n, to sort numerically. And we're going to sort lengths.txt as the thing that is being sorted. And so what this does for us is it sorts numerically these lines. So we've got bubbled up to the top methane, our smallest molecule, and then down through the largest, and then the total is our largest line numerically that's present here. So that's sort of one way to get at it, but maybe we've got enough files that we're sorting in this way that it goes way off the screen because we have dozens or hundreds of them, and so we can't see what the top one is. It's not even available if we scroll backwards. So why don't we store this information to an intermediate file, and then we'll introduce another command to grab the start of that file so that we can grab just only the information that we want. So we'll recall this previous command, and then we will, again, redirect it we'll say sorted dash lengths dot txt. Run that. And again, things are redirected instead of being presented here. They are stored in this file. We can cat sorted lengths.txt. And then our third command that we're going to introduce here to grab only that first line can be head dash n1. So head grabs the first couple of lines of a file. You can specify how many it grabs with the dash n. We want to grab only one line, just that top file name and its length. And then we want to do that for sorted lengths.txt. And then in a few steps here, we've been able to get to methane.pdb, where again, if you're operating on a large number of files, this would be difficult to access otherwise. But this is a little inconvenient to create this intermediate file at every step, especially if we know ahead of time what we want to do. So we have a way to, instead of creating these fiddly intermediate files, we can directly combine commands and do what is called pipe the output of one command into the input of another command, which will then operate on that and will produce the output that you want. So for instance, we could replace these last two steps here of saying sort-n lengths.txt, redirect that to a file, and then on that file perform this operation. We could say sort-n lengths.txt. Now we use the pipe operator, which is this vertical bar. For me, it's shift under backspace on my keyboard. I think it's shift on backslash for most keyboards that I'm familiar with. And then what that does, it says we're going to take the output of this command and pass it to the next command that we type after the pipe. So we'll say head dash n1. So sort lengths.txt, don't print that output yet. Instead, pass it to this next command, which will operate on it, and then this will print the output that it gets from operating on that. So if we run it, then we get in one fewer steps with one fewer intermediate file required, the methane.pdb answer that we were looking for as our smallest molecule. Now we could also combine the first two steps and not need a lengths.txt. We could say wc-l asterisk dot pdb. And we had previously stored that to lengths.txt before. We could instead pipe that to sort-n to directly sort the output here. And so we get immediately the sorted output, don't have to create an intermediate file, and that's quite handy. Further, we can combine as many pipes as we would like up to a very large character limit on these commands. It's somewhere in the thousands. I don't know it off the top of my head because I don't bump into it very often. I'm going to say I'll pipe the output that we printed here, and we'll instead pipe that to head-n1. So we're doing our word count of all of our PDB files, we're sorting numerically, and then we're grabbing the very first of that numerically sorted output, the first line of that. And so with this command, we can immediately come into this directory that contains all of these PDB files and run this and understand, methane is the smallest file by number of atoms here. Apologies, I have to step away briefly for just one moment. I will be back in under a minute. All right, sorry about that. I just had some background noise, needed to make sure wasn't going to become an issue for us here. So when we combine these three commands together, we can directly answer the question, which is the smallest molecule represented by these PDB files. And we could, for more complex workflows, if we have the appropriate tools to chain together, have this be an arbitrarily long number of piped together commands for whatever it is that we need to accomplish. I do also want to, while we're here thinking about redirection and piping, I want to show you the different behavior of a couple of these redirection operators. So we have right now length.txt. If we cat length.txt, this has just the raw output of that wc-l that we originally started with. Now you might wonder, like, why did we need a second file for this? Why didn't we just overwrite this with assorted lengths to reduce the number of files? So I'll show you what happens to sort of intentionally elicit some bad behavior. Here, we'll sort-n lengths.txt, and then we will redirect this to lengths.txt. We'll run that, and it runs as before. But then if we cat lengths.txt now, it's empty, which is not the intended behavior. We wanted to see these sorted rather than having a file that's fully empty. This is not useful to us. And this happens because with our single redirection operator here like this, the first thing that happens when we run this command is a new empty file called lengths.txt is opened, which overwrites the previous lengths.txt file. Then sort-n of lengths.txt, the brand new empty file, is run, and that's an easy sort. It's empty, it's still empty, and then we get lengths.txt, the empty file saved as the result of this, which accidentally erases the work we wanted. So be careful when you're doing your redirections here, because if you overwrite the same file that you are operating on, then you can run into behavior like this where you get the wrong answer or unreliable answers depending on like what system you are running the command on. Not all systems will perform this operation first. They might perform it partway through the command, depending on how they prioritize task order. And so you can get something that looks like it might be right, depending on how large your data set is, but omits something by accident. So do not redirect into the same file that you're operating on. I had also mentioned that there is a different operator that we can use to append to files. So we've seen the echo command a couple of times. I've used this to put hello on screen and some of our return times. So we can the echo command prints text. So we say echo and then some string afterwards. And then whatever string we have after echo is what is printed to the command line. So we can use this to create some text to redirect. So if I say echo hello, and I don't redirect it, as we've seen before, this will say hello on the terminal here. If I redirect this with the redirection operator that we've seen so far, the single greater than sign, to test file 01.txt. We don't see anything output on the screen, but we do have that hello stored to test file 01.txt. If I go back and I rerun this same command again, nothing prints to the screen. If I run cat test file 01.txt, it's still just hello. No matter how many times I run this, it's just creating a new blank file and then putting hello in it, overwriting it over and over again. Sometimes that's what you want to do. Sometimes it is not. Sometimes what you'd rather do is append to the file. So every hello or every new line is just added to the end of it. So to do that, we might say echo hello, and we'll use two greater than signs as a redirection operator. This will be test file 02.txt. And again, nothing is printed to the screen. And if we look at the contents after running it once, we've created a new file that has the contents in it. If we go and we run that, and we look at the contents, we have 2 hellos, 3 hellos, and this will continue until we run out of disk space or we get bored doing it. And so this is appending to the end of the file. You want to be careful, again, when redirecting to a file that you are operating on, because, again, the order in which the things are added and the operation is performed is fuzzy, depending on where you are running this. So you can get inconsistent behavior. Better if you need to redirect to a different file and use that instead of hoping that you luck out with when the append actually happens. So we'll go ahead now, and we're going to look at another sort of example workflow with our fictitious marine biology data. So we'll see ls-f, we want to cd into North Pacific Gyre, and then we want to cd into the folder for the date containing our data. And it has a bunch of these txt files, which have what looks like a standardized naming scheme. And these contain the data for the assay that has the relative abundance of these 300 proteins. So something that we might check is, what is the length of all of these files? So the relative abundance of 300 proteins, probably about 300 lines. We wc-l asterisk .txt, so we only want to look at these .txt files. We'll get output that looks like this, where, yep, most of them are 300. There's one here that's sort of jumping out at me as a little bit odd. And they all end in an A or a B, except for a couple that I'm seeing ending in Z. We can say, okay, so if we assume that we have thousands and thousands of these files, if there's one here that jumps out at us as not having enough lines, that means it can't have all of the data we want. So something is amiss here. Let's see if we can find any other files that are incomplete here that do not have all 300 lines that we expect for a complete data file. To do that, we can perform a similar piping operation where we say wc-l asterisk .txt. We'll pipe that into sort numerically, and then we'll say head-n5 as our final step that we're piping into. So we're going to sort all of this. We're going to grab the top 5 lines of that sorted output to see if there are any other files that have fewer than 300 lines. We see here that nope, it's just this one file that seems to have something wrong with it. And so we can pull that aside and see what happened with this run. Do we have that extra data somewhere? Or does this have to be omitted? Or can we use this partial data somehow? Whatever we need to do with this incomplete data file that depends on our specific domain. And we can say, okay, I hope that none of our files have more than 300 lines, because that would indicate that more data in there is in there than I expected. So something would have gone wrong with the assay, at least the output of the assay machine. So I can modify this command. We'll hit up to recall it and replace head with a new command, cleverly named tail. And what this does is similar to how head takes the first however many lines, tail takes the last however many lines. And so since we're already sorting these numerically, this will grab the last however many lines of our word count output, and we can see if any of them are larger than 300. And we can see we have our total line, which is larger than 300, but then the actual files themselves are all 300 exactly. So we don't have any files with extra data. That's good. Good sanity check to do. But we see this file in there that ends with a Z. So let's say we know that all of our files should have an A or a B associated with them by convention of how this particular lab collects data. And Z would be used to indicate a sample that has some missing information somehow. And say, okay, so what other files do we have here that are missing some information? I say ls asterisk z dot txt. We've got these two files that seem to be missing some information that require manual remediation. Go back, find that information, maybe rerun the samples, maybe pull them out if the information is not available, but they're flagged for whatever operation we need to perform. We could, in theory, if we knew that they were bad, we could just delete them right now. But maybe they contain some useful information. We don't know if we should delete them yet. So what we'll have to do later is, be careful to not select these for any particular analysis that we perform. And for a demonstration of how a wildcard could do that, we can select all files that end with either A or B .txt using an additional little bit of wildcard syntax. So we say ls asterisk, and then we'll use our square brackets, AB dot txt after close square brackets. And what this is doing is it's saying match all files that start with 0 or more characters in this initial position, then end with either A or B .txt. And now this is the set of files that we are confident have at least all of the information that we expect to see in terms of tagging, let's say, for our file naming convention. And so we could use this type of wildcard to interact only with these files if we're doing our analysis later. So another example of how we can use some of these tools to start doing sanity checks in a semi-real world-ish type of workflow. What questions do folks have about this material before we proceed? Apologies, I'm being signed out of my Google account during the middle of our... Okay, we're back in. Perfect. The length how many things can be inside the brackets. I believe that comes down to the number of characters that you're allowed to type in a command. We can certainly add a third one if we want to grab those Z files in there. Don't know how many characters there are in the typable data set. I don't know if you'd run out of characters to put in there before you would run out of character limit. But it's a large limit for how many things you can put inside of there, like hundreds or thousands. Absolutely. Again, if other questions occur to folks, please feel free to drop them in the chat. Otherwise, we're going to continue to look at another tool that we can use for creating some automation here of repetitive tasks. So we're going to cd dot dot ls dash f cd dot dot again ls dash f. All right, now we're back in our sort of data folder here, and we will cd into creatures is where we would like to be for our next example. I'm going to go ahead and clear. We'll pwd data shell slash creatures. We'll ls dash f to see what is involved here. So let's say that we want to get like some summary information for each of these three .dat files. Let's take a look at what's in them to start. So we'll say head dash n5, just grab the first 5 lines from each of basilisk.dat, minotaur.dat, unicorn.dat. And we can see, based on these first couple of lines at least, that for each of them we have the common name for this creature, the scientific name, the classification for the creature, when this data was collected, sometime in the 1700s for each of these, and then some genetic information for these mythological creatures. And let's say what I want to do is I want to get only the classification information for each of these files, and just have that printed out each on its own line, because maybe I want to grab classifications for all of the creatures that I'm looking at here, and include that in some other summary file. And again, we'll imagine that we're in a situation where maybe it's not just 3, we couldn't just copy and paste what's on the screen sort of thing. So we want to build up a tool that will do this in a scalable way, so it doesn't really matter how many we have to work with. The same form would be just as appropriate for working with 3 as with 3000. To do this, we're going to want to introduce the concept of a loop, which I'm going to do with some pseudocode right now. Pseudocode means this will not run, but it's going to be descriptive of the sort of the algorithm that we are walking through here, highlighting some of the syntax with plain English. So the particular type of loop we're using here is a for loop, and the keyword to start it is for. In this case, we'll say for thing in, that's another keyword, list of things. Then I hit enter, and you'll see my prompt is a little different this time. I get this greater than sign rather than the dollar sign, indicating that the shell thinks I'm not done typing this command, which is true. There's more that I need to type in order to have a complete for loop. So I will type do as my next keyword. Now I'm going to indent a couple of spaces just for clarity. This indentation is not required by the syntax, but it's visually nice for presenting it to a group or for having it as readable in a script. So I'm indenting a couple of spaces, say head dash n2. Or, I'm sorry, I skipped ahead a little bit. So we'll say operation using is our fictitious command for our pseudocode. And then we'll reference thing as our keyword here with a dollar sign to access the value of thing. Then we'll go on to a new line and we'll say done. And when I run this, it's going to throw an error because there's no such command as operation using. And so it tells me a such command is not found here. But we can talk through what the loop was sort of intending to do as written here. So the loop has the keyword for, in, do, and done. Between for and in, this is what we're going to call our loop variable. This is going to be the variable that as we pass through each thing, each element in the list of things that we provide as our next element after our second keyword in. This is some list of files, some list of words, some list of something. Our for loop is going to take each of the things in that list, and it's going to run the body of the loop, that is what exists between do and done. It's going to operate once using thing taking the value of each of the list of things. So if our list of things was basilisk.dat, minotaur.dat, unicorn.dat, thing would first be basilisk.dat, and we would run operation using basilisk.dat. Then we would run operation using minotaur.dat as the next element down the list. And then finally, unicorn.dat, if that was our last element in the list. And to reference the value of things, we're setting a variable here with thing. You get the value of a variable in bash by prefixing it with a $sign. So we're saying the value of the loop variable right now, which would be the file name in our example here. And we do operation using that file name. So that's our pseudocode example. It hit an error immediately, so it broke before it worked all the way through. So let's use an actual working example with more appropriate variable names. And actually get our classification out of each of these files. So we might say for file name, so we're choosing a different, more appropriate name for our loop variable. It's going to contain each of these three file names. So we'll say for file name in our keyword again, basilisk.dat, minotaur.dat, unicorn.dat. So I'm explicitly providing this list here for clarity. We can then say do, then again, indenting for clarity. Now is where we get the head -n2 on file name. We want to get the first two lines of these files to grab the classification. But then we want to pipe that to tail -n1 because we only want the classification line. So for each of the files, we're grabbing the first two lines, and then we're sending those two lines into tail to grab only the second line in the file. Sort of snip out a particular line that we want. And that's all we want to do in this particular case is grab that classification. So we get to our next line and we say done. And so we can see that we have these three lines of output where head -n2 of file name has run in sequence on first basilisk.dat, minotaur.dat, and unicorn.dat, and we get the corresponding output from each of the files printed to our screen here. We could, if we so chose, use a different variable name for our loop variable here. We could call this temperature or banana or X. But it is generally recommended to use a short but descriptive name like file name here because that's describing what we are operating on. I might also consider creature in this particular case. That is because when we look in a little bit about saving this stuff to a script for future use, when someone comes in later and wants to read and understand what you've done, having something here that makes like logical sense with the operation you were performing makes that a lot easier. You save yourself a lot of hair pulling if you try to write this as close to a meaningful sentence as you can. Don't make yourself in 6 months to a year try to figure out why you chose banana just to be funny here. It's confusing for no reason. Similarly, avoid the urge where possible to use single character names because sometimes as these scripts get longer and more complicated, you might want to know where else a variable is being used. Like you're using it here in a loop, use it later to do something else. And so you search the file for wherever that variable name occurs. If it's a single character, you'll not only get the variable name, but everywhere that the variable name letter is used. So every occurrence of X, for instance, in your file, which will be in some words, some of the variable use, and it's just more difficult to read. So again, these short descriptive names are preferred for a couple of reasons. All right. So we can extend our loop a little bit, and we can also pull in some of the previous shortcuts that we have used. So I said we want this to be extendable to, like, if we had a lot of files, 3 versus 1,000, it should make a difference. I'm not typing 1,000 files here. So instead, we can use our wildcard to produce our list. Say for file name in *dat. And then we can say do. And then let's expand the body of our loop a little bit. Let's first say I want to echo file name so I know which file I'm looking at. And then we'll do something else inside the body of the loop. We're not limited to a single command. We can do as many commands as we need to inside the body of the loop. And so we'll grab dash n 100 of file names. We'll grab the first 100 lines of each of these files. And then we'll snip out tail dash n5 of those. We're getting lines 95 through 100 of these, each of these files printed out after the file name. And then we'll say done. And so what we get is we get a snippet of this genetic information that is labeled each chunk by the .dat file name for the particular thing. If I were doing this for like visual parsing, I might also echo like some sort of visual indicator here, like a line of asterisks as an additional echo here. So I could quickly parse between each of the sections. And I would be free to do so if I wanted to add an additional echo command in here, because again, we're not constrained in the length of the body of the loop. Let's actually explicitly do that to make the point as well. We'll say echo. I just want to echo a bunch of asterisks. And then we'll echo file name. And then we'll say dash n 100 file name l dash n5. Done. Oh, I've accidentally done an error. Okay. So here's an important thing to keep in mind with echo. Unless you enclose the arguments to it, the string you want, in quotes, it's still being interpreted as components of a bash command, so it expands. And so what has happened is my wildcard expression of I want any file that has 7 or more characters has expanded each time to the list of files that have 7 or more characters, which is not exactly what I wanted. It does provide a visual separation, so I've accidentally gotten at what I wanted, but that's not quite useful. So I'm going to hit up to recall this. The formatting is a little bit messed up in this case, which is one reason why we might want to store these in a script rather than just run them on the command line like we're doing right now. But this is short enough that it's parsable. If I enclose this in quotations, now this should be treated as a string. And I hope when I run it this time, now I get just this visual separator, which provides a clear indication to my eye where each file begins and ends. Now, the point that I intended to make with this line was that this line doesn't have anything to do with the file name variable, whereas our next two lines are actually operating on it. You are free to have code inside the body of your loop that doesn't actually utilize file name or the loop variable at all. You can simply use the number of things that are in your list as some index cap for how many times you want to perform a particular operation. I could say, have this loop for file name and asterisk.dat do echo this string done, and not have either of these lines, and it would just give me 1, 2, 3 lines of asterisks. Not very useful in this case, but there are workflows where doing such things would be potentially beneficial, and so it's an option to you. You do not have to use the loop variable in the body of the loop. Another place where we might use this is if we are wanting to create backups of all of our files. So let's clear this and we'll ls-f, we'll say, okay, I'm going to perform some operation on my .dat files, like, trim some section out, remove a line, add a line, something that changes the file where it sits. And I want to have a record of the previous file in case that goes wrong, so I can restore from the original if I need to do so. A way that you might think to do this using CP would be CP asterisk dot dat. I'm going to say original dash asterisk dot dat. Right, I want to copy each of my files to a corresponding file that is named original whatever the file was dot dat. But instead we get an error because what CP is doing is for all but our final command here, or our final argument here rather, this expands to our list. So it's the same as saying CP basilisk.dat, minotaur.dat, unicorn.dat, space original dash asterisk.dat. And CP is like, okay, if I'm copying a bunch of files, the final argument that I'm given has to be a directory. Because otherwise, I'm copying a bunch of files over the same file at the end. Like, no one actually wants to copy 3 files one after another, overwriting the same file name. And so it prevents us from doing that because that's simply not a workflow that people want to do. And if you do it by accident, then you're destroying data potentially. So what we need here is a loop instead, because the CP command will not directly do that for us. So we could say file name in asterisk .dat. We do, and then we say CP file name to original dash file name done. And then so now we're going through one by one and composing a set of 3 copy commands that copy from each of basilisk, minotaur, and unicorn.dat to original dash basilisk.dat, original dash minotaur.dat, original dash unicorn.dat. We don't get an error this time. And if we ls-f, we see that we do indeed get these original files produced. So copying like this is another way that we can utilize a loop. Maybe starts to help you think about the types of loop workflows that you might want to approach. We've already covered spaces in names earlier in response to a question. But just for the sake of completeness here, I will say, no, let's assume we had 2 additional files here that someone else gave us that were titled red space dragon.dat and purple space unicorn.dat. If we wanted to access those files correctly, in our loop, we would say for file name in red space dragon.dat or space purple space unicorn.dat, enclosing the file names that contain spaces in quotes so that this is an entire entity and these are not being treated as 2 elements of our list here. We can say do, we can just say echo file name here and done. We don't actually have these files, but it gives me red dragon.dat and purple unicorn.dat. If I recall this, get rid of the quotes, and rerun that same loop. So we're rerunning the same loop as above, but I've gotten rid of the quotes around these. This is being parsed as red, dragon.dat, purple, and unicorn.dat, which is not what we want. So if we had those files in our collection of .dat files, we might, instead of saying for file name asterisk .dat, and then treating it simply as a sort of trusted input, what we might do is enclose our variable in quotes. Oops. And I've added an additional .dat here. So that should be just echo file name, close quote. Because I didn't do that, we have an extra .dat. But what this does, as we're processing variables, if there is a space in one of these variable names, this protects our internal command to the body of the loop from being confused by spaces present in it. So when you're processing a group of files that may include spaces, best practice is to enclose references to that variable in quotes. But I've accidentally also added a little suffix in this particular case. I hope the example is clear, however. Then we have one more loop example. We'll CD into our North Pacific Gyre example again. We're dealing with each of these files that contain our relative abundance of the 300 proteins. So we had previously established that we were interested in only looking at the set of files that ends in A or B to process. So we could say for data file in, and these are going to start with this particular prefix, nil nemo, in case there are other folks who are collecting data in here. And then asterisk AB .dat, so any .txt rather in this case. So any files starting NENE, then containing any characters, then ending with either A or B .txt, we can do. And maybe we're not confident in how we want to sort of compose our command yet. So we'll start off, I just want to echo the data file and done. So we're just going to see this, the set of files that we're operating on listed here. And it's this list of files, visually inspect it, we'll say, okay, we're probably good to go. And I will recall this. And what I'm going to do is now sort of compose part of a command that I might want to run. We'll say, I want to echo data file, and then I also want, eventually I'm going to run goostats on this, and I want it to take as input data file and as output stats data file. And maybe let's actually compose the full command here. So we'll echo bash goostats input output. And so what this will do is it will give us a list of commands that we could potentially run with this loop if we go back in and we remove the echo. But by including the echo, we see, okay, we're going to be running this full list of commands. We're running bash goostats, the input, and then the output is this distinct file name that's prefixed with stats for each of these. And if I hit up again, I can go back and say, let's get rid of the echo. And now we will actually run goostats with data file and stats data file. And this use of the bash command and then the name of a script is something we're going to look a little bit more at in a moment when we look at creating our own scripts. But this is how this is one of the ways that you can run a set of commands that you save to a file. So you say bash, run the contents of this file, and that file may take some input. In this case, it takes the file name that we want to process and then the file that we want to write out to. Run this. It will take a little while to run, as this particular set of stats takes, I believe, 30 seconds per file. I don't want to wait 30 seconds per file. I don't have that many minutes worth of stuff to say. So I'm going to hit Control C to cancel an in progress command, which is another good thing to know. So if there's a command that's running that you don't want to allow to complete because it's taking too long, or you realize, oops, that's not the command I wanted anyway, just hit Control C and it will stop and you'll be back to the prompt. And we can see ls-f that we have some of these stats files created, but not all of them yet. It looks like it was faster than 30 seconds in this particular case. So I interrupted the command partway through with some of these stats files created by hitting Control C. That's also how you can exit if you're in the middle of creating a loop and you're like, oh, actually, like it's waiting for more input, but I've already messed up this first line, or I've changed my mind about what I want to do. You hit Control C, and it will exit you out of the loop syntax and drop you back to the basic prompt. So Control C to cancel or exit an in progress command, either that you're still typing in this case, or that is currently running in this case. Questions about loops? Saving output once it is run. So like saving, scroll back. So we're talking about saving like our creature output in this case, or are we talking about the saving output of like our script here? Creature output example, all right. Because in the script example, the output is being saved as these output data files because of the script, which is a case that's sort of independent of the loop stuff. So if you want to save output here, then what you can do is redirect the output to a file. So we'll say so cd slash creatures ls. All right. So we can say for file name in asterisk.dat do, and then we want to echo, we'll put a bunch of hashtags as our visual separator this time. And we will save this to output.txt with our double redirect. And then we will our file name, and we'll enclose this in quotes, again, for best practice in case one has a space in it. And then we will redirect this to output.txt. And then we can do our head dash n100 file name again, incorporating our enclosing in quotes here in case there's a space. And then we'll pipe that to tail dash n5 file name once again, enclosed in quotes, and we'll redirect that to output .txt. And then we can do done. And this is a fiddly way to do it, where you're providing your redirection at every line. And then if we can't output.txt, it contains all of the information that we would expect there. But if, for instance, you're only interested in saving some of these elements, you don't have to redirect everything to output.txt. So you're printing some things to the screen, some things to output, can be a handy thing to do occasionally. In terms of saving the output of a loop that's already run, sort of. So if you are able to view the output on your screen, like if it's still visible when scrolling back, you can copy and paste from a terminal. So I can highlight all of this, copy it, and then paste it somewhere else if I'm so inclined. But if it's larger than the terminal can hold, then unfortunately I'm out of luck. And I believe we can also, if we want to redirect the entire contents of a for loop by, instead of having each of these redirects from output.txt, I'll not retype the entire thing, but let's say, well, go ahead and edit it. So I'm removing these redirects for each of the steps. So this will be printed to screen again. And then we'll modify it one more time just to capture all of it. That was the fiddly way to do it with the individual line redirects. This prints it to screen again. Then I believe if we use a redirect operator after our done, then this will capture the entire contents of the loop. I don't do this frequently, so this is a bit of an experiment. Output 01.txt. And hey, it did save the whole thing. So if that's an appealing way to save what's going on, you could do it that way as well. But yes, if you are producing like very large amounts of output, printing it to a file rather than to the screen is probably a better way to go. Because if it overflows the screen, you can't copy it, you also can't read it, right? So that hasn't been a very useful thing, probably. Cool. Other questions about loops before we continue to shell scripting? Seeing none, go ahead and move there. But again, if questions occur, please feel free to drop those in chat. So we'll say c dot dot f, and then I want to cd into molecules. And I want to clean up these .txt files. I don't need these in here right now. So I'm going to model good behavior with rm. I'm first going to ls *.txt to get a wildcard expression that matches these txt files that I want to delete. And then I'm going to recall that command. And I'm going to say, okay, yes, those are the files that I want, just my txt files that I was using as intermediates. And then I'm going to replace ls with rm. And these files are now gone, leaving me with only my PDB files to work with, just to clear up our space here. All right, so let us create a shell script, where a shell script is a file that contains some list of commands with some additional bonus syntax to allow us to take input of different types when we use the script, like we were just seeing a moment ago with goostats.sh. So we will use our text editor Nano to open up a new file called middle.sh, where .sh is the file extension that we will most frequently use for bash shell scripts. So nano space middle.sh, and we're going to create a new file by this name. Now, one thing that a shell script can be is simply a command. In this case, head-n15 octane.pdb, if I can get the right key there, then tail-n5. So this, we're not being particularly clever with our command here with respect to scripting. All we're doing is taking a command that we might otherwise run on the command line to grab a chunk out of the middle of octane.pdb. And this will be a valid shell script. So I'll go ahead and Control X to exit. I'll hit Y to save the buffer because I'd like to save this contents. Then I'll hit Enter to confirm that I want to write it to middle.sh. And then if I want to run that script, as we saw with goostats, I will say, use the bash command. So bash, run the contents of middle.sh, interpreting the contents of it as a series of commands. And that's relatively straightforward in this case. It was a command that was run. We get a middle chunk of octane.pdb. And we've saved that command in middle.sh so we can rerun it exactly as we ran it before whenever we would like. We can hand it to another researcher if they want to get the middle of their octane.pdb file at some point in the future, then they could use that to do so. And that's called like a hard-coded script where there's no way to modify the behavior of your script at runtime. You might have a list of such commands that will do for a particular set of input that you provide it with like an octane.pdb file. It will always produce the same output, and there's no fiddling around. You're dealing with it. These are useful for things like making figures oftentimes. But we can make this a little bit more flexible if we want to. Let's say what I actually want out of this script is not just to get the middle of octane.pdb. I want it to get the middle of any file that I pass it. So let's use nano to open that file back up to make it more flexible. So we'll say nano middle.sh, and this will, instead of creating a new file, because this already exists, it will open up the existing file. And we're going to modify the script here by removing that sort of static octane.pdb reference. And we're going to replace it with a variable enclosed in quotes. So we've seen that we want to enclose variables in quotes if we're not necessarily controlling what the file names are, in case there is a space or a special character. And this is like extra good practice in a script because someone else could use this on their data where you definitely have no control over the file names. And you'd like it to work well for them. So, and then we're using a special variable, one, which is a positional variable, which is the first argument after the name of the script when you say bash middle.sh space and then type something else. That first space separated something else after the name of the script is going to be substituted in here for $1. So we could run bash middle.sh octane.pdb to get the file, to get the same behavior that we had a moment ago, or we could run bash middle.sh pentane.pdb to run it on a different file. And if we wanted to provide like numerous positional arguments here, this could be a 2, a 3, or a 4 if we're providing like a long list of things and we want to select one of them out of it. We just increment that number as we proceed outwards. But in this case, we're getting the middle of a file, and so we only want to provide one file name, and so we only want that single positional variable. So having made our change here, we'll go ahead, Control X to exit. We'll hit Y to save, and then Enter to confirm the file name. And then if I run bash middle.sh again without providing an additional argument, I get an error because I've changed how the script operates. So I need to provide additional information in terms of that positional argument. So first, let's provide octane.pdb so we make sure that it works the same as it did previously as a sanity check. We provide the same value as input as was previously hard-coded, and we get the same output. So hooray, it at least works for that. But what if I instead run bash middle.sh pentane.pdb? Well, I get the middle chunk of pentane, which is similar but different in terms of these positional components. And so we're snipping out the middle of a different file. And any file that has enough lines that we can snip out the 10th through 15th to get that middle of it there will give us this the same sort of output. Now, what if we want to make it more flexible? Like we don't always want to grab lines 10 through 15 in one of these files. We want to be able to specify which middle chunk we snip out of our file. So let's modify our script a little further. Say nano middle.sh, pull it back up. And then we'll say, let's add additional positional arguments. I want to be able to provide how many lines we're grabbing with head as one of my additional arguments. And then I want to get how many lines we are snipping with tail as an additional argument. So this is going to look like bash, some file name, then some number, then some additional number, which will allow us to flexibly snip out chunks of any file of our choice for some definition of the middle that we provide. So we'll save this and we'll demonstrate how this works now. Again, Y to confirm after hitting Control X, and then enter to confirm the file. Now, I'm going to say bash middle.sh, pentane.pdb, 15 and 5, because we want to see if we can get back the same behavior as before. And this does indeed work. We could grab a later chunk of the file if we say 20-5, so we grab the first 20 lines and then grab the last 5 of those, so we're getting lines 15 through 20. Or we could grab fewer lines if we so choose. So we can now sort of flexibly snip out chunks out of any file that we provide as an argument here. But this is also getting maybe a little bit difficult to remember. Like, I know what it does right now, you know what it does right now, we just wrote it. That's fine. Me from 6 months from now is not going to remember how to use this, and so I would have to go in and parse the source of the script, which is inconvenient, and if this is a long script, it might take me a long time to do, and I might get it wrong. And that would be troublesome. So let's be nice to our future selves or our future collaborators and go in and add some documentation. To do this, I'm going to give myself a couple of lines to type in here, and we're going to add comments, which, start with the hashtag or the pound sign or the octothorpe. The name of this character that you use depends on your context and your age. But whatever you call it, this is the symbol that indicates this is a line that a human will read on the script, but the computer, when running it, is going to ignore it when this is a bash script. So we'll say select line from file. Just to briefly describe what it's doing, because maybe middle means something different to me in 6 months. And then I'll give an example usage. I'll say bash middle.sh. We'll say file name. And then the number that we provide is the end line for the next one. And then it is the number of lines for the next one. So this would give us a hint if we come back and read these first couple of lines of the file, how we would use this to snip out the center chunk of a file, or indeed any chunk of a file that we want, using a command of this format. So we'll go ahead and hit Control X to exit, Y to confirm, to confirm the file name. And now we've got ourselves a friendly little middle.sh script that we can use to snip out chunks of files that also contains documentation on how to use it so that we do not have to tear our hair out 6 to 12 months from now. All right. So that's our first script. What about, though, if we want to have a script that processes a lot of files at once rather than a single file? So we're not going to be able to use positional arguments and say, I want to be able to do WC-L asterisk dot PDB and then sort -n. I want to do this type of operation where I can have a wildcard expression or a list of files that I provide that is arbitrarily long. So this could have 3, 6, 100, 1,000, however many elements in it. How do I make a script that can then operate on all of these? I can't use positional arguments, or I bet there's a way I could, but it would be a pain to write. So instead, we will do it in a friendlier way. So let's make ourselves a script that can do this in a more generic way. Use nano to open up something that we'll call sorted.sh. And we'll start off with our comment. We'll say, I want to sort files by their length. And then I'll also provide the usage up front because I know how this will work. So we'll say I want the usage to be, we'll run the script with bash sorted.sh, and I provide it with one or more file names. This is an arbitrarily long list of file names. Let's say WC-L. We'll have something here, and then I want to sort -n after we have counted the word, or counted the lines rather, in all of the input that's provided. And what I want here is an expression that will give me all of the input following sorted.sh. And bash provides us a nice little shortcut for that, which is $@ This is all arguments after one or more file names. And again, we're putting this in quotes in case any of these contain spaces. But this is a similar special scripting syntax that bash provides us. One means the first thing after, $@ means all the things after. And so we're passing the whole list of all the things to word count and sorting them. So we'll Control X to exit, Y to save, Enter to confirm. And I can say now bash sorted.sh, and I can say *.pdb, and it works as it did before. I can also say, I can leave that .pdb, and I can say, let's add all of our .dat files from the creatures directory up above and sort those in as well. And I can add in everything in writing as well. That's a file. And so I get haiku.txt in here. And then these are directories, so they're not parsed in the same way. So we get some zero length and some bonus output. But it's still running my WC on all of these. And so I have this very nice flexible script that I can just, give as many files as I like as an argument, and it will sort them by their length and as defined by number of lines. All right. So one more way to get a script that is useful to you. So we've been doing a lot of sort of experimental demonstrative stuff on the command line today. And doing that sort of interactive experimental workflow is a common way to figure out sort of what you want to do for a more permanent workflow. Or try a few things, see what works. And maybe the last few commands that you ran worked and you want to save all of those and use those as the starting point for your script. So let's pretend like I just created figure 3 um, in my paper that I want, and it was the last, say, 4 or 5 commands that I ran that were important to do that. That was the successful effort. So there is a command in Bash called history, which prints out a list of all the commands that you have run up to some limit. Again, it's like 1,000-ish, and it depends on the host you're running on sometimes as well. But this will give you all the recent commands, at least in the current session. And we don't want all of those. We'll say I want the last, just the last couple. So we'll say tail dash N5, and the tail here will include this last command as well, I believe. Then we're going to redirect that to redo figure3.sh. So if I want to rerun those exact commands again in the future to remake figure 3, I can do so. That, and then we say nano redo figure 3.sh. And we can see that it has given me these last 4 commands that I ran prior to the history command, as well as the history command, and then also the indices on the list of commands. So to turn this into a proper script, I have to go through and delete those prefixes because those numbers are not proper code. And then I don't actually want this one because that's the command that creates the script. But pretty quickly, I'm able to grab those last handful of commands that I ran and edit them down into a file that I can rerun in the future to recreate the exact workflow that I just performed. And so that's another way that a script can be useful. Now, these ones aren't particularly useful commands for us for making a figure, but we'll make believe here. So again, Control X to save, or to exit, Y to save, Enter to save at that file name. And now we've got a couple of scripts that do a couple of things that we created in a couple of ways. Let's see here. Another example script we could do for Nell's pipeline. But in the interest of time, let's omit that so that we can get to some of the additional advanced topics. If you are interested in an additional scripting example, it is near the bottom of this page in our course material under Nell's pipeline, creating a script. It's not doing anything especially novel. It is reinforcing a couple of the concepts that we've just seen with scripting. But the example is there if you are interested. So what questions do folks have about scripting before we move on to finding things? All right, seeing and hearing none, I will go ahead and move on to a couple of ways to locate stuff using the command line for a couple of definitions of stuff. In particular, we're going to look at how we can find content inside of text files that matches particular patterns. And we're also going to look at how we can find files and directories whose names match and some of their properties match simple patterns. So to do that, where are we right now? In molecules, so we'll cd dot up into writing. ls-f. We have haiku.txt, data, thesis, and tools. Wonderful. So we'll go ahead and clear. Then I'll run pwd again if we need to orient ourselves. And let's go ahead and use that cat command to print out the contents of haiku.txt. This is the contents of that text file, a triplet of haiku. And so this can be kind of a fun example for pulling out specific content that matches different patterns as this is written. So the particular tool that we're going to be using to grab lines that have patterns matching some input we provide is called grep, which stands for GNU regular expressions, I believe. Definitely regular expressions. I'm not as sure on the G. And what this is going to do is take some expression, so some regular expression, which is its own category that goes beyond what we can cover here today. Can make regular expressions very complicated and flexible and specific. We're going to do just some relatively fundamental things with them here today, but know that it can get more complicated if you need it to. And so the way grep works is we say grep, we provide the pattern that we want to match, and we provide the file that we want to look for it in. So I want to find lines that contain not in haiku.txt. So we'll say grep space not space haiku.txt. And then we get these lines with the pattern that I put in not highlighted in red, at least on shells that support displaying color. Let's see. Now we can also demonstrate that grep by default searches in a case sensitive way. So we can say grep, we say capitalized the as our pattern, and we're going to look for that in haiku.txt. And we get this the that starts off this line is therefore capitalized, and then we get the capitalized the in thesis, but we don't get the line it is not the true tau because this is not capitalized. We do not get in the presence. Also of note to us is that this isn't properly the word the, this is the as a part of thesis. Maybe we want to find whole words that are match our pattern. So whole words that are separated by spaces. I can add the -w option here to say, give me space-separated words that match capitalized the here for haiku.txt. And now we're no longer matching my thesis, and we're just getting only this one line here. We can use that whole word boundary on phrases as well. So we can say grep -w. And for phrases like this, we need to enclose them in quotes, because again, that space matters to bash. And so we need to say, no, this is a pattern enclosed in quotes. So you get today is not working. This is treated as a word that is being grabbed out because it has space separation around it as well. Another option for grep that we might sometimes be interested in is knowing like where in the file these lines actually occur. So having line numbers can be helpful. You can say grep -n to get line numbers. Look for line numbers that contain it in haiku.txt. Now we get the line number and the matching line. Now, like with other commands that we've seen today, grep can take multiple of these options to modify its behavior, so long as they are not conflicting. So we can say grep -n -w for lowercase v in haiku.txt. And so we get our lowercase these here. We get the line numbers for them. And if we want to get rid of that case sensitivity, we can do so by adding an additional option, say -n-w-i for case insensitive. Now we also get the capitalized the in this case and the associated line numbers. And we are also able to, if we want to, sometimes it's what we want to do is not grab the lines that contain the pattern that we're providing. We want to grab all the lines that do not contain the pattern we are providing, because maybe those are the ones that contain error information or something. We provide the -v option that inverts the results. So instead of getting all the lines that do match, we get all of the lines that do not match this. And so we get this subset of lines that do not contain the whole word the with any case. And you can get really quite fancy and complicated with grep. The way you compose these expressions, these regular expressions, was like a vastly expanded wildcard system where you can provide a lot of positional information for different categories of character. Again, that goes well beyond the scope of what we're able to cover today. But I want to make sure that flexibility is at least folks are at least alerted to it. And we can get quite a bit of flexibility as well just by looking at what is available from grep if we simply provide additional options. Or we can see some of what we've provided here, like inverting the match, get these line numbers, see some of the options we've used, and a number of ignoring the case, a number of options that we have not used. And you could imagine composing ways of finding particular patterns that you want if you want to have a good regular expression that is well composed, and you specifically tailor how grep is searching for and grabbing lines matching or not matching that pattern. So that's grep for finding text within files. Let's now move on to looking at find, a different command, which finds files themselves and directories as well. So we'll go ahead and clear. So my cursor was stuck for some reason. I had to hit Control-C, and now type clear. And let's start off by using find in its sort of most default mode. We say find, we provide a location we want it to find in, which we'll say is this directory, which is the writing directory. And what it's going to do is recursively list all of the files and directories and their relative paths compared to the this location that I provide. So we can see that it shows our data directory, it shows a couple of files inside data, it shows haiku, it shows our thesis directory, some contents, a tools directory with some contents as well. Now, this in and of itself is already maybe useful as sort of a recursive LS that gives relative paths, but we can get a little bit fancier, actually substantially fancier. We'll start with a little fancier. We'll say, I want to only recursively find directories here. Let's ignore all the files in the output, just show me the directories. So we'll say find dot dash type D. So we're giving this this option, and find is the first tool we're seeing that's deviating from the sort of option syntax we've seen before. It's a weird tool. You'll occasionally run into weird tools like this that have a slightly different interface. So we might usually expect to see dash dash type for a whole word option. Find specifically takes only dash type in this case. And when we run it with that appropriate syntax, we get this short list of all of the directories that exist here. So data, thesis, tools, and then tools/old. So a directory called old exists within tools. Now I might be interested instead in finding only the files here, not the directories. So instead of type D, I could say find dot dash type F. And now instead of getting the directories, I'm getting all the files contained therein. So we'll show an intentionally caused error next here. So let's say I'm looking here for all files that are named something.txt. So say, yes, based on what we've learned so far, we'll say find dot. We can say dash name as our new find component. This is the option for find that allows you to specify a file name or some pattern for a file name. And I want to find anything that matches asterisk.txt. Say, all right, wonderful. And I expect that should match some of the stuff in data and also haiku.txt, but it's not going to work. So let's see how it goes wrong. And so what's happened here is find, again, is behaving a little bit differently than some of our other tools. And it is immediately expanding this wildcard expression. And so it is saying, rather than parsing this as a wildcard that's being taken internal to the tool, it's saying expand it. So we're going to say this now equals haiku.txt, which is the same as what we would get if we said ls asterisk.txt. So it expands out in the same way, and then we find everything named haiku.txt after it's expanded out. And there's only one file here that matches that. In the same way that we've done before, we can sort of get around that premature expansion by enclosing in quotes, say, no, pass internal to the tool this wildcard and use that as the pattern to match against. So if we do this correctly, then it actually is able to recurse and look for the contents that match .txt in the subdirectories, which are this Little Women 1 and 2.txt. Another way that find is a little peculiar is the way that you can operate on its output. So you might expect like, oh, I could simply pipe the output of this to WC-L and use that as an input for some sort of sorting workflow as we had done before. That doesn't actually work, again, because of sort of the weird syntax that find provides. And so instead, we have a different way of passing find output to other commands. So let's say we did in fact want to word count the number of lines in each of these star.txt's, matches to star.txt. So we'll say WC-L, and then we're going to enclose in $ and parentheses the find command that we want. So find dot name and in quotes asterisk .txt. And what this syntax is doing is saying, all right, bash, execute this first, get the output of this, and then substitute the output of this command contained inside the parentheses for the expression here. And then we're going to run wc-l on that output. Again, a little different than what we've seen before, but it's because find is a little strange. And you will encounter other tools that are occasionally strange in the same way. So good to see how we might deal with them here. And we see that works more or less as we expect, getting the word count, or rather the line counts for each of these txt files and then totaling them up. Now we can combine grep with find in this way. So if we want to like search particular files for a particular string, so I want to look for the pattern FE inside all of the files, starting one directory up. So we're looking from data shell. And I want to look at all of the files that are named .pdb. So I'm looking for iron atoms in .pdb files is basically this expression. And it's able to find for me up in that folder data inside data shell, there's a subdirectory PDB. And this heme molecule here has an iron atom as one of its components. And that line matches my grep here. So yeah, another way to sort of combine off of find. Find also contains its own syntax for executing a command on each of the results that it has. Dash dash help. And its help is also a little weird. Let's see. Yeah, so this is one of the ones, again, because this command is a little strange, that you might want to look on the web for some documentation that might be formatted in a slightly more human readable way. What I was looking for here is the exec component, where if you want to run something on each of the results, you can use find wherever you're looking, plus whatever the pattern dash exec, and then with the particular bracket syntax. But that's like very specific to find, and sometimes it is more convenient to simply say like, I don't need to learn exactly how find does what it does. I just need to wrap the output in something that another tool can use. And that's where this $ parentheses syntax comes in handy. But as is often the case with composing these workflows with shell tools, there are like a dozen ways to do the same thing. And find does provide an internal way to perform an operation on each of its results with this exec component. Just to mention that to folks in case it is useful. Do we have any questions about finding things? I will say for both find and grep, while you're getting started with them, places like Stack Exchange can be excellent resources because probably someone has tried to do the kind of thing you're trying to do before. And so you can sort of template off of an existing example. Seeing no specific questions, let us go ahead and briefly look at remote access to other systems, and then we'll have a couple of minutes left to look at our software environment. All right. So remote access to other systems. So depending on how you gained access to your shell session today, you might have already done some of what's covered here. But if you just drop in via on demand, or if you're running something local on your machine, then this might be some useful content for you if you need to connect to other systems, like creating a connection from your local system to the cluster, for instance. Uh, and what we're talking about here when we're talking about remote systems is other computers that are connected over the network. Um, that can be the UMN network that connects the computer that you are running on your office via Wi-Fi and then some internal backbone to the cluster. Or it could be connecting to something that is available to you over the internet as a larger network. And we're going to today be looking primarily at connecting to things that are MSI related. All of the ideas transfer. It's just we're thinking about MSI stuff today. So when we want to connect to a remote system, we need to know some way to identify it. And that's going to be either a host name, some other web address, or the IP address of the remote system. At MSI, we're primarily going to be working with either host names or aliases for those host names. Um, so the main cluster that we're dealing with in general is agate, and it has a host name agate.msi.umn.edu. We can see if that host name is accessible from our particular computer by using the ping command. So we'll say ping agate.msi.umn.edu. And we get some output where ping is sending a set of small packets of data and then asking for a quick response from agate. I'm going to go ahead and hit Control C because I don't need this to run forever. But what it's doing is it is sending, again, these small packets and getting a response, and you can see how long it took it to respond. Not very long in this case. Now, if agate was not reachable, we might see something like an error message. So I'll intentionally elicit by saying, let's ping fake.msi.umn.edu, a system which should not exist. And indeed it does not. So for ping, we're getting name or service not known. So there's nothing by this host name that is available to us. You can also have a situation where like the host name is defined and it starts to try and send some data, but then there's no response. That indicates there's some network problem between you and the system, or the system itself is experiencing trouble and is not able to respond. Those are circumstances where you might want to contact the help desk to see like what's going on. Is there a problem with how I'm connecting? Is there a problem with the host I'm trying to connect to? Because it's not something that we're necessarily able to debug ourselves as users. But if we have a host that we are able to ping here, and we know that we have an account on it, we can create a new shell session on it by using the SSH command, which stands for secure shell, which gives us an encrypted connection over which we can run commands on that remote system. The syntax for it is you say SSH, and you give your username on that system, which for me is done 0404 on agate. You can say then when you give the host name, agate.msi.umn.edu. So I'm trying to connect as username at this host. And I'm able to do so. I get this nice welcome message that says, please leave if you're not supposed to be here. And then I have a slightly more detailed shell prompt here that contains some of the customization that I have added that is convenient for me when I'm running on the cluster. But I still have that $sign. I can still run ls, which again behaves a little bit differently because I have an alias set up on the cluster. Now, you may be, depending on the system you're trying to connect to, prompted for a password. and you may be prompt for a two-factor authentication as well, depending on where you are connecting from. So keep those elements in mind. We do have the ability, if you are frequently connecting over SSH to one of MSI's systems, we have some documentation on how to set up what are known as SSH keys. And I'll drop that in chat here as well. Send that, which allow you to bypass the password component, but do not allow you to bypass the two-factor authentication component. Now, if I want to disconnect from this remote system, I can either type exit or I can hit Control D. I'll type exit here because it's visible on the screen. And now I've been logged out. I'm back to the previous shell prompt that we have been using prior to now. So this connection to Agate was like a sub shell, a new connection that existed inside this previous connection that I was running. We can sort of exploit that a little bit to our benefit. If we want to use SSH to like simply connect to a remote system, run a single command and exit immediately so that we get the output of that on the remote system here. We could say SSH username at hostname, so my username at agate.msi.umn.edu, and then we enclose a command in single quotes. And this will run that command on the remote system. So I still get the the welcome, please leave message, but I also get the PWD that happens immediately after I log in. So this is my home directory on the system, and I'm currently on the system right now with this other shell session. So my home directory there is the same as where I'm currently running it. Now I can chain a couple of commands together if they're quick and short, if I would like. So I can say, give me the current working directory and also the host name that I've connected to, which is a new command that we have here, which will just identify the name of the particular computer that you have connected to with your SSH command. And it's getting angry at me for doing this now. All right. All right. So this is something I'll have to update for next time. So we're not allowed to do that anymore, apparently. I think it is. So just run the host name. Yes. All right. So we can't chain together multiple commands anymore, which is probably for the best, because then you start composing things that will be troublesome for our login nodes in terms of how long they take to run. But this is new behavior to me, so I'm not exactly sure why or if there's a different syntax that is expected. But if we only run hostname here, we can get that is running on AHL02. Agate head login node 02 is what we had particularly connected to there. And then I will also, if you are connecting via SSH, sometimes you will want to send a file to the remote system that you are connecting to. This is not like super meaningful for the particular way that I've got my shell set up right now. Because right now I'm currently running on AHL03. That's another Agate node, and all of those share the same file system for your home directory. So I don't actually have to copy files from this machine to the next machine. It's all living on this shared storage solution. But let's say I was connecting instead from my personal desktop. and I wanted to copy haiku.txt to the cluster so that I could do something with it. I could use a command scp, stands for secure copy, haiku.txt, and then the syntax is username at hostname, and then colon, and then you give it a path that you want to copy it to. And I'll just copy this right into my home directory, tilde/, and that is also giving me trouble. Oh no. Well, this is not ideal. Let me see if this is just giving me trouble because I'm connecting from within Agate. So I'm backing out. So I had a shell session on a different node. This is my personal desktop. So I close out a couple sessions. I'll clear, touch, the file and temp, my file .txt, called scp temp, my file .txt, done 0404 at agate.msi.umn.edu, and we'll try and copy that to my home directory from here. And it wants a Duo authentication, which I will answer on my phone. And this one allows it to go. Okay, so something was preventing me from SCPing from an agate node to another agate node, which isn't something I would want to do. It's odd. But what I've just demonstrated here is SCPing from my personal machine to agate, which is the actual thing you would want to do. You have some file, myfile.txt, that exists. Maybe it's a big file full of data that you want. You say SCP, the file on the current machine, then the user at host and the location you want to copy it to on the remote machine. You can also flip these if I knew the location of a file on agate that I wanted to connect to and download to my device. So I could say scp 0404 at agate.msi.umn.edu. I could download haiku.txt and copy it to the current directory, again answering this Duo prompt. Such file or directory. Okay. Well, I don't know quite what's going on there. Apologies, my SCP material is not working as I had expected. And this is quite new to me. Well, let us proceed on to the next section. Apologies for the remote access stuff being a little messy. SSHing to a different host. I called it my file, not Haiku. Excellent. Good looking out. I'm just going to make sure it works for my own sanity. Okay. And now we have my file.txt. Thanks.